and her group. And secondly, we couldn't have time to summarize day one. From that perspective, I would like to ask you just to finalize the work from yesterday, to finish with the report of the workshop which we conduct, and then for 10 minutes to summarize the day. From that perspective, the participants of today will be familiar what happened with yesterday, and if you are interested, actually all lectures uploaded already on our YouTube channel, and you can watch if you are interested what we spoke and what was presented yesterday. Dan, you agree with my plan, and after that we will continue with the second day program.
That works fine for me, thank you.
Okay, I understood that we have some delay of the sound. Now it's okay. I hope that everything is fine now. Then Gergana, are you here? Finally,
yes,
you're here.
Good morning, good afternoon.
I know that yesterday you conducted great work. Please to share your thoughts and to share what you've done yesterday and how finish this workshop. Okay.
Yes, sir. Thank you. I believe you can all hear me well. So again, good morning and good afternoon, depending on where you are on the globe. So my name is Gergana Vaklinova, and I'm the section head for the Concept Development and Experimentation Center section at the CMDR COE, and I'm also serving as the center's gender advisor. Within our section, we have a specific thematic portfolio, which includes the topic of climate change. And we've been dedicating some targeted efforts into studying and exploring this very broad and very important matter. So what happened yesterday was actually we conducted the first CMDR COE workshop on climate change implications on military activities, and specifically our discussions were focused on what future for CMDR, or crisis management and disaster response. Now, before I move to the specifics of our work yesterday, I should like to mention that we were heavily building upon a newly published report by the North Atlantic Civil Society Working Group on Environment and Security, and we were actually looking into their recommendations for sustainable peace and security in a changing climate. So this was, in a way, directing our discussion. And I was very happy to see a number of very experienced SMEs in climate change and in related topics from both governmental and non-governmental organizations taking part in this first in a series of workshops on climate change and the work of our center on this matter. So without further ado, I would like to share with you the process of our work. And we started off by framing our discussion, opening up the perspective first and examining climate change and its root causes, and also the effects and impacts, direct and indirect, it has on security. And you will see that we all agree that climate change is a significant security threat that requires international and collective response. But before I get there, before we got there, we also went through how would climate change affect security in the future, because this is an important perspective that we need to be able to already discuss and build some foresight into. Then we also, of course, focus the discussion more on the role of the military in addressing climate change implications to security. And here Of course, we had a twofold focus, one looking internally, so mitigating own impacts, and also externally, so what are the impacts on military activities. So we were discussing both of this, if you wish. We took both of these perspectives. Finally, we of course wanted to relate climate change to crisis management and disaster response, and specifically disaster response, and even more particularly in terms of prevention and preemption, as you will see from our key takeaways. So this was the first part of our discussion. And of course, after some short lead-ins by all of the participants, there were a number of other follow-up questions that came around, and you actually see them on your screens. So we had a very interesting discussion in terms of whether climate change is a shared responsibility, and I can share with you that we had an overwhelming agreement that it is a shared responsibility, an international threat with local specifics. We also looked into ensuring equal participation in planning, decision making, and response, and this is also linked to one of the other questions that you see on your screens, and that is how to actually ensure a population-centric approach to the assessment of risks, vulnerabilities, and threats related to climate. Certainly, after being able to provide and to come to such an assessment, we then discussed how to make sure that the recommendations are integrated at the strategic, operational, and tactical levels, respectively. And of course, we also discussed resilience, societal and military resilience, and we were also very much looking into the importance of targeted funding away from traditional military spendings on traditional capabilities and to more capabilities that are linked to building and increasing resilience. So this was part two. And finally, the results from our discussion, and of course we had 2 hours, 15 minutes to arrive at key takeaways, and these are certainly not exhaustive. And of course, 2 hours are definitely not enough to address all of the interlinkages with other topics, for example, protection of civilians, gender perspectives, and the like, human security. But of course, this was an attempt at to serve as a starting point for our discussions. As I mentioned, we plan on having further events of the sort. So these are our conclusions, and shortly you see what you see on the slide. I will not repeat it. I will just add to the first point, and I think I already mentioned it. We see climate change, and we reached a group agreement that it's an international problem, however, requiring localization and contextualization depending on what we are looking at. And importantly, this also links, it is linked to the necessity of ensuring ownership, local ownership. We discussed that climate change and agreed that climate change is stemming from ecological disintegration, and particularly the aggressive extraction and consumption of resources, of which energy resources. And we also looked into the indirect and direct impacts of climate change. And of course, we discussed for the direct impacts, death and injury, and then for the indirect, poverty, competition, displacement, and of course, conflict. I forgot to mention that there was a group agreement on the multiple cascading effects and orders of consequences that climate change has on crisis management and disaster response, and on the life and well-being of populations. Then we moved, our next key takeaway is that climate change is a security issue that requires cooperation and exchange for collective response. And therefore, we more or less gathered around the idea that it's a collective responsibility that also requires a specific mindset in terms of policies, in terms of strategy, that would then allow for the development of specific capabilities that are linked to climate and environment. And we also found out that there is not enough training, especially in NATO, concerning climate change. And also that funding should be tailored and targeted in terms of resilience, building and increasing resilience and respective capabilities therefrom. Finally, key takeaway, population-centric approach and looking into a climate-related risk, vulnerability, coping mechanisms assessment. And here, that is also linked to the understanding that the human environment should be understood from a population-centric approach. And especially here, relevance has gender mainstreaming and the integration of gender perspectives. Finally, we all agree that NATO will not and perhaps would not be in the lead on climate change, but certainly there is a role for the alliance, which requires and merits further investigation, which is our goal for the next events that we are planning on conducting. And with this, of course, there's more than that, but I think this is more or less the essence of our discussion. So thank you very much, sir. This concludes my presentation.
Very valuable thoughts and very good for what you already propose, and I'm very satisfied from this workshop because it's really important for us to see how and what how we to be prepared for the future, especially from the center point of view. Thank you very much. Just to finish the conference, first day of the conference, I would like to summarizing in conclusion the first 4 panels of our conference. And I would like to recapitulate again the presented assumptions from yesterday. Our keynote speakers highlighted of climate change on the individual state actors and non-state actors, and of course on military activities. As Mr. Dirk Dubois illustrated a scenario from sub-Saharan Africa and the Sahel, where we'll have heavy losses to agriculture in a region that is already struggling to feed its population. Thus, militaries have already mobilized to deal with radicalization and conflict caused in part by climate change stresses. Mr. Jean-Dominique Dullier, in support of his statement, stated NATO will continue to adapt its assets for extreme climate conditions and is seeking to improve its search and rescue technology and warfare across its domains. The same confirmation was made by Rear Admiral Taman, who pointed out the NATO Climate Change and Security Action Plan as a comprehensive military stock, taking all climate-related activities. Mr. Jordan Boujilo from the Sofia Security Forum put a stress to the health as a subsistence being threatened by climate change. We all agreed that increased poverty and malnutrition are leading to increasing gambles. In such direction was the presentation in our first panel, where Mr. Benjamin Wallace stressed attention to the fact that information on future conditions is complex and limited. For example, modeling uncertainty, and they are cascading impacts which are the second layer of complexity that's often ignored nowadays. On his turn, Mr. Ceushevich, pointed that the threat multiplier characteristic of climate change will increase problems such as government instability, the spreading of diseases, conflicts over material supplies, strengthening of radicalism globally, and widespread migration as well. Similar address was made by Dr. Radostina Primova, as she pointed the emerging geopolitical and security issues in response to climate change challenges. Dr. Primova has drawn attention to the excessive dependence on the raw materials and the strategies for supply chains related to food security, human rights, and socio-economic impacts on local communities. Very interesting was to hear from Dr. Kyprian Alexander Kuzera a study to what happened on an isolated island due to the exploitation of the nature and change in weather patterns and their correlations to the violence that caused. This had provided a distressing example how this phenomena can shape and impact our future. Our third panel yesterday was focused on enhancing resilience in the aspects of climate change challenges. Mr. Joel Thomas discussed the essential role of private-public partnership in supporting national and community resilience, and pointed out on the modern private sector-led approaches to prepare the whole society from neighborhoods to nations. In light of it, Dr. Konstantin Tsetsus demonstrated the ongoing European Defence Agency research project for common operation picture in disaster and crisis management. Actually, there are a lot similar with our technical architecture, which we already made it here in the center. Now the European Defence Agency started to work on this one. I'm joking, of course. While Major Streeter showcased as the German National Terror Hub project. Professor Kostadinov related the direct effects of the climate change driven processes to their second layer of impact, the operational one, the human factors, as well as components of the medical resilience. Colonel David Bates in his lecture presented an examination of how online human factors as well as components of the medical development of organizational capabilities. Dr. Walter David showed us the correlation between climate change and conflict, which is observed in the countries enduring conflict. In the last session, which one was extremely interesting, Mr. Kyle King underlined that we must enhance each national capabilities towards resilience, as well as our renewed efforts to build more resilient communities and enhance societal resilience. Mr. Steve Recker and Dr. Joe Green from the Hawaiian Center provided their thoughts on how the military would react to the climate change. Now they are contributing to the resilience, as the challenge is how do we reduce vulnerability. Mr. William Hanham from Euro-Atlantic Disaster Response Coordination Center presented the climate change issue in the perspective of the NATO's civil emergency response mechanism, as it's dealing with calamities coming from disasters and climate change. And our distinguished guest from Jordan, retired Colonel Zuhair Tamimi, made an overview of the national adaptation plan in regards of climate change. I'm glad to add to his presentation that Crisis Management Disaster Response Center of Excellence is taking part in assistance to the Jordan's National Center, which is fully engaged with strategic control and coordination among all actors in these NATO partner countries, and our cooperation will continue in future with a lot of common events. Speaking for partnership was the accent in the lecture of Stefano Bergoncini from Stability Policing Center of Excellence, who presented us the role of NATO stability policing in environmental protection. Most of these lectures you can watch, actually all of them you can watch on the YouTube, our YouTube channel, CMDR COE YouTube channel. But most of these presentations, which presented actually the articles, will be published in our proceeding, our annual proceeding, and hope that this year it will be published also in Springer edition, which we will continue, of course, on the second day, and most of the articles will be also published on in our proceeding. We, together with Deputy Director of the Center, we would like to thank you once again to all lecturers, and I really do hope yesterday's presentations were beneficial for the whole audience at our 9th annual conference. I'm sure that today we will surprise you with additional topics which and relations to climate change, and we can see how space weather environmental modeling can be assessed and can be take in consideration about the relation between the space weather and the climate change issues here on the Earth. I'm sure that after this panel, we will be very familiar with all this. Deputy Director, I think that we can close the yesterday's session and to continue with the second day.
Yes, sir. Allow me also
Yes,
to
of
add
course.
that from the quality assurance perspective, I want to assure all colleagues and lecturers and everyone else participating in this conference that we are actually getting even better from time to time, and it is a promise that our next conference will be much more interesting and joyful also.
I really hope, and actually it's a very good opportunity because this is our second event after COVID situation, and this is in hybrid mode. And believe me that we cannot compare actually with online events because we see live people in front of us and their reactions and questions asking and etc. It's a much more interesting. Okay, that was for the first day. With that, we will close this session. And Dan, now is our turn as moderators to continue with the second day with presentation. Today we will have around 8 presentations. We will starting with space weather environmental modeling, and Colonel Daniel Galton will present it, head of the Operations and Coordination Division. Actually, you are not anymore in Science and Technology Organization, I think so, but you have opportunity to present yourself. After that, we will continue with space weather effects on satellite navigation. Dr. Jens Berderman, you can see the agenda on the slide, on the screens. With Dr. Vasilev, we will talking about space weather surveillance and tracking. Using of artificial intellect, it will be interesting to share their thoughts by Lieutenant Colonel Konstantin Lazarov and First Lieutenant Gutierrez Gwen. And actually a lot of thoughts, food for thoughts we're expecting from this lecture, and to start on discussions on the session. We're expecting also Supriya Chakrabarti and Professor Mauro Messerotti and Dr. Tzu Wei Fang from NOAA to talk about space weather forecast with operational impacts. This is our, again, very with a lot of new information, but not to lose time, like not to happen like yesterday. Actually, we have some kind of problems technical with blackout, electrician blackout, and that late our. I will not lose more time and give the floor to Dan. Dan, please, the screen and floor is yours, and to start this session.
Okay, so thank you, Arlen. Good afternoon, good morning, everybody. I appreciate your attendance here today for this discussion. And I also appreciate the invitation to be able to kick things off in the second day. So my intent for today's discussion was to provide a little bit of an overview. So you will see a few slides for those that have been here throughout the whole discussion. I provided an update back in January, and I will leverage a little bit of that, but I want to discuss kind of where we've been and where we are going. I think it's great to kind of set the stage a little bit for the things that are going on, but I also think it's probably more important to think about where we are going. So as you see in front of you, see my less than stellar, very serious biography, my great picture looking very serious. A little bit about my academic background. I'm a space physicist by education for the Air Force and now the U.S. Space Force. I am an acquisitions officer. I built small satellites, built large satellites, done manned space flight work, worked at the European Astronaut Center, worked closely with NASA. I've done a lot of different things. I have a little bit of an operational background, a little bit of test background, so quite a bit within the space community for my 23 years of military service. So it's been a great 23 years. As Orlin mentioned, I'm in my last days at the STO, specifically at the Collaboration Support Office. So I'll be moving to take command in the Air Force Research Labs at their basic science research portfolio for the Air Force and also for the Space Force. So exciting times, but I'm still staying involved with NATO. I'm working on the space activities, of which I'm co-chair on 3 different activities and chair of a different activity. So great times. I'm looking forward to staying involved, but that's enough about me. Can we go to the next chart, please?
Thank you, Dan, for this one. By the way, who is the host now on the WebEx? Colonel Dimitrov, maybe. Let's start then with the next presentation.
So Orlin, I put together 9 or 10 charts to brief. I sent them up yesterday to Rally, and she had sent them up. So if we can pull them up, I'll keep it very short because I see I only have 20 minutes. But my intent, as I mentioned, was to provide a little bit of background about how we got to where we are today and where we are going. So if we can pull the charts up that I sent forward.
Could you repeat?
If we can pull up the charts that I sent to Rally yesterday, she was sent them to the IT.
Yeah, exactly what I'm talking. And Ralica, could you upload the
Okay, great. Thank you. Like I said, I will keep this relatively short so that we don't go too far over our time constraint. And again, so back in January, I provided a brief overview of what the space weather is and why it's important and kind of where I think we should go. And so what I've done is I've updated my charts. For those that will see the charts, there's a little bit of a repeat, but I think it's important for those that are relatively new for us to discuss kind of where we've evolved and where we should be going. So next chart, please. So again, I'll provide a little recap for those that are not space physicists or not really understanding what space weather is. I will keep that relatively short, but it's important. It impacts our operations. And as we've discussed before, space is more than just a unique domain. It is intimately tied to the other domains: cyber, maritime, land, and air. Space is one of the 5 operational domains as identified by NATO, right? Where we want to go forward, what is our strategic intent? In other words, what are we trying to do? I'll try and get to the heart of that and try and be as simple as I can. When you heard me talk in January, one of the things I tried to do was come up with a couple next steps, right? I call it a recipe for success. That is a checklist. For the operators in the room, a checklist is very important, right? If you do step A, then you do step B, then you do step C, you're guaranteed to have success. Well, I will give you my thoughts in terms of what we originally had and where I think we are going. What I'll do next is try and provide a little bit of an overview of the tools that we've seen so far. So provide a snapshot of some of the space weather models. We are dependent upon space weather models, but I don't want to make this all about modeling and simulation. It's important, but yes, it is just a tool. I will then offer up just a few ideas for where I think we should go and then kind of the next steps forward or our homework. And then as any good presenter does, I will open up the floor if you have any questions. So next chart, please. So really, I will keep this simple on the next 3 charts. It is a little bit of an overview on space weather, right? So hopefully by now, everybody should be aware of what space weather is, right? So just to summarize, space weather really refers to any kind of change around the Earth terrestrial system that's caused by the sun. So we have an outflow of hot gases that come out as a result of the nuclear fusion that takes place within the sun. So we have very fast electrons and ions that are emanating. They come very fast. So we also, they're at multiple hundreds of kilometers per hour as they come out. And so as that impacts the Earth's magnetosphere, we have a very complex, dynamic, interactive system. And how that system changes and interacts, right, drives our space weather. Next chart, please. So at a very basic level, why do we care about space weather? Well, it impacts everything that we do. All of our systems are impacted, right? At a very understandable knowledge level, right? If we start at space and move into the terrestrial, into the Earth, right? Anything that is in space is impacted by that solar wind, right? We also have radiation that's taking place. It's a very harsh, dynamic, complex environment, but it is not for the faint of heart, right? So any astronauts that are out there have the possibility of being exposed to radiation, right? And that's the same for any kind of hardware, any satellites that fly up there, right? We have all kinds of effects that take place on satellites, and on the next chart, I'll get into a little bit more detail in terms of the impacts on satellites, right? But it really impacts all of our systems. As we move closer to the Earth, right, that radiation impacts our pilots, our air crews, passengers in the plane, right? You're getting a dosage as you get higher in the atmosphere, right? And you're into the atmosphere, right? But you're being impacted by all of those. At a very basic level, right, solar events or space weather effects can have the possibility of impacting us. We see it with the northern or the southern lights. It also has the potential to disrupt our communication capability as it impacts the atmosphere and it changes. And we also have the ability to have impacts to our power grids. We discussed previously some of the impacts from previous solar events have knocked out power grids. And so all in all, we need to have plans for what we do moving forward in the event that there's bad space weather. Next chart, please. Now, one of the reasons that we wanted to look at this in more detail and why I put this tab forward, right, is the impact to our operational satellite systems. Right, so we've discussed a little bit in terms of the effects of radiation on aviation, and so it is really can impact our pilots, can impact passengers. But the things that we are focused on here is the impacts on the satellites itself. So when you have energetic events taking place, or you even just have simple basic physics that's taking place, energetic particles hitting the satellite systems, right? You have the ability for energy to be deposited. You can potentially end up with single event effects, which are impact, right? So you see these effects upon the molecules of the satellite. You have internal charging where you can have a discharge between the systems. Electricity is never anybody's friend, right? And so these are things that we need to be aware of as we look at mission planning, mission concept. But for our piece, what we are looking at is the operations piece. How do we plan for these events? And what do we do to maintain capability so that the warfighters in the other domains are impacted to the least amount as possible? In other words, what are our contingency plans? What are our courses of action as our operational capability may diminish through these space weather events, right? So the 3 charts I just had should hopefully calibrate, should set the stage for where we are in terms of why space weather is important. So next chart, please. All right. So I will not spend a lot of time on this. This was the initial recipe. This is what I put forward in terms of where I think we need to go forward, right? Understanding the space weather models, that's an important piece. What do we have? And probably more importantly, where are there gaps and where there are opportunities to work with other researchers, right? Collectively within the North American communities, as well as within our European communities, right? The one thing I will continue to stress in the piece that we need to continue to think about is how do we bring our space operators into these discussions? People that sit on consoles have to plan for this, right? And we've listened to several briefings from our colleagues in terms of how they look at the space weather models and how they react to it. And I think that's a great first step, right? And then as we've looked at this, we wanted to focus potentially on those operational impacts. And then looking at what others are doing, what are other agencies, other organizations doing to translate those science and technology requirements or the strategy to action plans. So next chart, please. So what I want to do is I want to take a step back now that we've looked at that, right? We've talked quite a bit and we've been very fortunate to have a lot of briefings. And what I've done is I'm looking at a lot of the material that's online, different research papers. Here's a brief summary, and this is not meant to be read in great detail for the non-scientists or the non-space physicists that's in the group. This is not meant to make your eyes water and your brain hurt. But what it is really intended to do is provide for you a little bit of insight into all the models that are out there. And I would say this is not a complete set of the models that are out there. But as we discussed, the systems, the sun, the magnetosphere, the Earth itself, the terrestrial aspect, the atmosphere, they're all interrelated, right? And so these models have certain areas that they focus on. Some models focus strictly on the sun, right? Am I likely to see a solar flare, a solar event take place, right? Do I forecast energetic particles? What do I do, right? Other models look at the magnetosphere, right? And just as a memory, right? Magnetosphere is your protective cocoon that's around the Earth as a result of the Earth's rotation and the Earth's inner magnetic core, right? The dynamo effect, right? And then others look at the ionosphere, right? What is that distribution of the particles and how does that interact? All I'm looking at here, are trying to provide for you, are snapshots. These are models that are out there. And so my recommendation for you, and I should point out too, that what I try to do is as a little key here, anything that has a plus are things that we have heard from our briefers, right? So I kind of notionally, and I took a little bit of academic latitude with this. We listen to DLR, we listen to DMO, we've listened a little bit to NOAA as well as some in NASA. And what I describe as system models, it's from end to end. So anywhere from solar down to terrestrial, they cover the whole gamut. And then simply anything that has a circle on it is open source code. So in a theoretical world, any space scientist could go out there and look to try and combine many of these models. And I think that's a great start for looking at specific things. But I will tell you, as a space physicist, as somebody now who builds satellites and tries to understand what's going on, this makes my brain hurt a little bit, right? And so next chart, please. So I've come up with a little bit of a revised recipe for where I think we should go forward. All right, so the very first thing is, I look at the names that are listed here, and I see a lot of the same names repeating themselves, and I'm very grateful for everybody's support. I would argue that maybe we need to go back one step, please. Thank you. That's perfect. So what I would argue is that we need to solidify our group membership. Are there people that we need to identify that should be a part of the group? I look and I see one of our NOAA representatives from the US side. I know we have had our Air Force Research Lab representatives. We potentially could identify some from some of the different labs from across our individual communities. All I ask is that you think, are there subject matter experts that should be a part of the group that are not, right? So that will be a homework assignment that will come on your next chart. If you go to the second bullet here, you just saw on the previous page a whole list of different models. And as I mentioned, even my brain hurts a little bit when I think about that. I'm not sure that's the right way to continue to go. I think there's value in us listening to the models and listening to the capabilities of the countries. The labs within the specific countries, and there's value in that to learn. I think there's great interaction. I think we've already seen some opportunities for potential future collaboration. But where I struggle with that is, where do we go? When is enough enough? Right? Have we heard enough models? Do we need to continue on models? I think that's just something to think about. Right? The ultimate goal is not to combine all the models that we have. Right? That's one piece. I think it's to understand the model, but I think what potentially is more important is the impacts of the space weather, right? So identifying the models that we've seen, the models that we're aware of, are there things that we should do, so that we should focus on for research in the future? So just things to think about. And then again, my third bullet here, we just mentioned that. How do I tie the operation piece with our research communities? In other words, if I'm sitting on a console, how do I tie the operator to the research, to my scientist and engineer that is doing the work, right? You have to have those two communities tied. As we look down, I think the next two bullets are there's no change. But my feeling going forward is we need to start to prioritize what it is that we are looking for, right? So my intent and my hope for today's discussion, and I look at the agenda, is, you know, we are starting to focus more on interoperability, right? How do we communicate? How do we leverage existing services? From a space weather perspective, I think we're starting to understand the types of space weather information that's out there, the data, right? We've talked about KP, right? Looking at that logarithmic capability. How does that tell me how the Earth's the vertical aspect of the magnetosphere, or sorry, the Earth's magnetic field is changing in response to space weather, right? We've talked potentially about some of the other sources as well. Fluctuations of the magnetosphere, right? Those are important things, but I think what we need to do is start to transition from the science and technology piece and start to look a little bit more in terms of the operational aspect, right? So identifying what we have done so far is a great first step, and now start to think in terms of operations. The models are a tool. They're a data tool, in my opinion, right? They tell me as an operator, I love it from a science perspective. I love trying to understand. I would love a predictive real-time forecast of space weather. I'd love to see the integration across the various scientific communities in terms of where we could go. But it's the eternal discussion that we have as a military member, right? Take the science and technology, and it's the so what? Why is it important to me? You know, as I go back to command, you know, if I'm running a small satellite system, which is one of the activities we are potentially trying to do as a NATO alliance, I want to understand what space weather means to me. If I'm flying something in a geostationary orbit, it means something different than if I'm flying something in LEO orbit, right? In low Earth orbit. I have different physics that are taking place, and I'm concerned about different things, right? So to me, it's the so what question, and I think that's what we need to prioritize on moving forward. Next chart, please. Okay, so my recommendation is this. This is what I would consider your homework. And what I mean by your homework, this is everybody that is on the right-hand list. I'm looking at the number of participants, and I'll be completely honest. I am one of these. I'm responsible, so I need to yell at myself later. I'm not yet appointed by my nation. I just submitted my paperwork last week and waiting for it to get processed. So if you have not yet been appointed by your nation, you need to talk to your national coordinator. And this is me wearing my NATO hat still. I'll take it off later. But if you've not been yet appointed, each nation has its own process. So please do so. Simply, for the majority, some nations have it online, some have it where you fill documentation out and send it out. So please do so if you've not done so. There's a document that we uploaded on the on Science Connect and the shared website several months ago. I saw that it's out there. It provides a lot of the things that I think we want to focus on, and it's simply titled The Operating Concept of Space Weather Events, and that's in the NMSG-187 folder. At the beginning of it, what it does is it provides a little bit of a checklist, right? Again, going back to the checklist, right? And it simply says, identify a risk, identify a problem, identify a course of action, identify contingencies. And I think ultimately that's what we are trying to go to. Take the individual modules or the individual data inputs from our individual software, right? So lots of great software, lots of great space weather modeling tools. Take those outputs and combine them so that we have information, right? But again, that is a tool. What do we do with that information? What are the contingency plans? How do we push that out? How do you disseminate data, right? So pull all the individual national inputs in, combine them, figure out what that means, and then how do I push it out to the individual nations, right? The challenge that we have with space is that all these capabilities are primarily owned by the nations, right? It is a sovereign capability. Now, my personal opinion is that's not sustainable nor resilient, right? So we need to think about what comes next. So I will, as I start to wrap things up here, I'd like to challenge you. Who are the participants that we are lacking? Who should be at the table? Who should be part of this discussion that we do not yet have? Who do we need to solidify? I will challenge you, and please send Orlin and myself an email. Just this week, I reached out to ESA and talked to their Space Weather Center, some of the Space Weather Center researchers. I'm trying to bring them on board. I've had a few discussions with some of my NASA colleagues. I'm happy to reach out and engage. And I actually have a conversation tonight with University of Michigan back in the U.S. So I should have probably put it up. The framework that you saw in some of the space weather modeling is one of the products they put together, and it's just a recent output. So if you Google that, you should be able to find that. So I'm having a conversation with them this evening in terms of they've looked at a bunch of the models and how they combine them, right? So ultimately, that second piece is what products do we need to produce, right? Because I think it's good to have a report at the end of this discussion. I think it's even more important to provide those courses of action, those plans of emergency, those things moving forward. And then the last piece, of course, is the timelines. What do we need to do to make this activity successful? So, we do not need to solve all these questions today, but as you listen to the next 6 speakers, those are the questions that should be going through your mind. Who are we missing? Who do we have? Do we have the right people? What products are we producing? What have we learned so far? And more importantly, what do we need to build? And then what timelines do we need to execute these along? So next chart, please. That is it. That is all that I have for you. So that 20 minutes that you just heard, and I'm very proud that it only took 20 minutes, so I apologize if it went a little long. But that 20 minutes that you heard today really recaps the last 8 months of work that we have done. So it's a snapshot of why we're doing it, what we have done so far, and where I think we are going. So with that, I will stop talking, and I'll open up the floor for any questions that you might have or any feedback or any thoughts.
Thank you very much, Dan. For now, it's very easy to start because I think that all participants are familiar what we are going to do and how is our next plan. As you understood, we will work this group for 3 years, and next already 2.5 years, we should provide all these answers of the questions which Dan already presented. Not to lose time because our timeline is so narrow. Please to start with the next presenter. I think that is on the slide. We will present my proposal is every session to be around 1 hour and half approximately. Next, we will have 8 presenters, with everyone to be, if it's possible, to be no more than 15, maximum 20 minutes with questions after everyone. If you have questions from who is presenting in the WebEx, you can ask your question directly. We provided also some opportunities for questions for our guests from outside who is watching us on YouTube, can ask his questions on the chat forum. And also we provided additional possibility to ask question when going on our website, CMDR COE, in the front page, there is a ask your lecturer, put code 46666, and you can submit your question over there. I will watching and can translate transfer the not to translate, of course, to transfer the question to the lecturer. Okay, not to lose time. The next presenter will be Dr. Jens Berderman, Head Department Space Weather Impact, DLR Institute for Solar Terrestrial Physics. You can see on the slide what is the topic of his presentation. Jens Berderman is head of the Department Space Weather Impacts at the DLR Institute for Solar Terrestrial Physics. He received a PhD on astroparticle physics in 2007 from the University of Rostock, and immediately after joined the German Electron Synchron ton. As a postdoc in 2011, he began his career at DLR, and since 2030 he has been head of the ionospheric effects and correction working group at the DLR Institute of Navigation and Communication until 2019. He is involved as project lead for the DLR contribution in several nations, as well as ESA and EU projects. His field of expertise is ionospheric research, with focus on monitoring, characterization, and modeling of ionospheric disturbances, space weather, and its impact on ground and space-based infrastructure. Furthermore, he is chair of the working group on ionosphere scintillation within the IAG subcommission 4.3 atmosphere remote sensing. Okay, Jens, can you hear me?
Yes, can you hear me?
Yes, we can hear you very loud and clear. Just before to start, I don't see any questions on the presentation of Dan, but if someone, there is, just a moment, there is a question. Okay, you can share your screen. Yes, just share your screen. And you can see the...
I already shared the screen. Can you see it?
No, not yours, Jens. There is a question on the
Okay.
presentation of Dan. I'm sorry for I missed this question.
No, that's okay. I was getting ready to type an answer. So I would say,
could you stop share your screen, please, just for a moment?
Yes. Okay.
Now, could you share your screen? No, not yours. I'm talking on my guys. Yes. This is from the chat. Actually, you can see Dan how far. Actually, you can see Dan. Can you answer on this question?
sure. No, I was going to make a quick comment, Orlan. Thank you. So the proliferation of technology has been pretty widespread. Right? Many of the products that we use as military operators are available open source. You can look at any number of different websites out there for some of the same data that we have. To be honest, I'm not sure the predictability. I'm not sure where some of our non-state actors are going. I think if it's for legitimate reasons, I think we all want to understand how space weather can impact our operational systems or the satellite systems. You know, that's the good thing about space being cheap is there are a lot of non-state actors now that are flying. That's also a challenge from a military perspective is there are a lot of non-state actors. So there's not an easy answer on that. I would say that there is a proliferation of technology out there. So if non-state actors would like to get a lot of the same capability, it's readily accessible.
Okay, thank you. My last asking to you, yes, so you can upload your presentation. My asking to everyone who is talking on through WebEx, because it's a broadcasting, please switch when you are talking or answer the question, please switch on your cameras just to be broadcasting live through YouTube. Okay, yes, the floor and the screen and everything is yours. It's your time.
Okay, thanks. Thanks for the kind introduction of myself, and also thanks for the introduction of space weather, which has already done in the talk before. I will now present some information on space weather effects on GNSS-based navigation. And there are effects on navigation due to changes of the space weather conditions. And there are two big effects. One is the plasma in the ionosphere can cause a delay of radio signals due to pretending an excess in distance between satellite and the measurement site. And this could be even stronger if you have strong gradients caused by solar storms, for instance, or ionospheric storms then as a result. And another thing is small-scale irregularities, which can be also connected to storms in the polar region, but also occur in the equatorial region. which can lead to scintillation of the GNSS signal at receiver level. And this could be very strong and even lead to loss of log. And then you might have not enough satellites to make a proper positioning solution. So these are, in short, the effects as a motivation. Now I will go more into detail on the effect of specific space weather events on navigation. I will start with an interesting period in 2017 in September. There was, it was many events. It was an activity period of the sun. So you had solar flares, you had radio bursts, and you also had some coronal mass ejection causing some geomagnetic storm conditions in the polar region. And I will start with the solar flare, which was a quite huge one, X9.3. Here, that's the second light in the SDO video. And this flare caused, hit the day side, of course, of the Earth. And at 56, you can see it right now, 56. Now you see it with yellow and red. It already caused problems for GNSS receivers, which we used here. It's a rate of tech change map in 1 minute resolution. And also the flare lasts only 3 minutes. We could detect the changes in the ionosphere and the effect on the GNSS receiver with the ROTI maps. So it was quite visible that the day side was affected and all, as you see here, all receivers, many receivers were affected by this event. Now looking more into detail on this event. So you see here again SDO, and you see the spectral band, which was 30.4 nanometers, and you see these double bang. And these the whole time was only very few minutes, 3 minutes. But you see it also if you look at the vertical tech, the total electron content in the ionosphere. So these are the receivers getting the information, the vertical tech information, have a connection to the satellite, get a measurement, and then you see it interrupted, and 2 times. So both peaks you can see here. So you lose the connection, many satellites, many receivers lose the connection to the satellites. And this, of course, has an impact on services and applications. One impact was the space-based augmentation system in Europe, EGNOS. So there was a reduced availability down to 75% due to this outage of the receiver. So then you cannot use this supporting system for aviation anymore, because for aviation, you need a high availability and high security. And this is another example. This is the precise point positioning algorithm. It's one of the precisest for really centimeter and level accuracy. And you see, you have it's very accurate. And then you have the event. You lose the connection to the satellites, so you lose your data. And the precise point position algorithm needs some time to get back to the original precision, to the centimeter level precision. Here you see it's went to 1 meter and more. So that is for many applications, it's already very bad. So if you make a precise measurement, you need centimeter level accuracy, and then such event could be traumatic. Here's the summary of the kind of solar flares. So depending can have a big impact on navigation, especially in the 30 nanometer UV band component. If you have there strong component, then you have serious effects on GNSS positioning. And it hits the whole Earth day side and can last minutes up to half an hour, 2 hours, depending on the flare. Then during the same period, there was another event. It was in radio burst, causing a lot of noise in the frequency range of the GNSS frequencies. And funnily, not all of them. So the effect was more on the new frequencies, L2 and L5. You see the signal to noise ratio. So the noise was very strong, and the signal was decreased strongly, so that you cannot get the signal out of the noise. And then this frequency could not be used for positioning. But nowadays, many precise applications need multi-frequency positioning. In that case, the other frequencies were not available, only L1. And if you have a multi-frequency device and you think you use multi-frequency to correct the ionosphere, in that situation, you have the full ionospheric error back because you only had available the L1 frequency. And in the precise point position argument, it was the case that the people who use precise point position only using one frequency, L1 frequency, have even a better positioning than those expecting multi-frequency, which they do not get. So this is very important to know. And though one has to be aware of such event and to know if you can trust your receiver your multi-frequency positioning solution in such cases. Then another event, 2014, caused by coronal mass ejection. So you have an ionospheric storm. You can see the bubble which forms in the polar, the disturbance are generated in the polar region, go down to equatorial region, and here you see such an additional ionospheric plasma which is formed in the polar region. Here you can see it even better, which caused gradients, and this again leads to problems for GNSS receivers. Here in that case, again, a space-based augmentation system was affected, the WAR system in North America. And here, this event lasts about 3 hours and caused also the non-availability of these augmentation system for aviation. So, and it's very important to follow such events, because if you know you cannot use the system, you might want to know when it is back and can be used again. So you have to follow when the event starts and when is the event over. And you might even want to know how it is regional. You have to be much more regional also in your modeling and in your information in future, I think. Here's an example how we try to access this with a disturbance index spatial gradient, where we try to build up an indice which is easily accessible by users without knowledge of many scientific terms like total electron content. It's just an index from 0 to 5. And here you see it's the famous St. Patrick Day storm, and you see how in the polar region the disturbance occur, move down to mid-latitude regions, and you see the regions who are affected very much, and you see when it's over, and you can give a precise information to the users in the different regions. And that's the aim in future, really, to say now we have problems, and now the problems are over in this specific region. Then I already mentioned there are other problems for GNSS, which are small-scale irregularities causing scintillation effects. I introduced already at the beginning. And here the famous Kindner plots, in which regions such as small-scale irregularities and scintillations occur. And very dominant is the equatorial region, but also in the polar region it occurs, and especially strong during storm conditions, ionospheric storms. And yeah, in the polar region is from north to south, you see the scintillation events. And in the equatorial region it's in the crest region here. You see it's all around. And yeah, this could last hours and could lead to that you, in the worst case, lose your signal. In other case, you have scintillations on your signal, and this might decrease your position and accuracy and your results. So you have to be aware of that. And there we also studied what is the impact on the GNSS receiver, because this is what you want to know, how strongly you are affected, at which times, in which region. And here we looked at the equatorial region and compared 2 different sites. One is in Ethiopia and one is in Japan, and almost the same over the northern crest region. And you see, if you go on local time, it appears at the same time, and during sunset hours, and lasts also for 6 hours mainly. And then you can also look how often you have loss of log with compared to the strength of the scintillation event. And if it's strong as expected, you have it much more often. And then it's also important to know for the receiver how long you need to get the signal back, the tracking back, and how long your tracking will be effective. If you lose your signal, it might not be a big problem if you're on a vessel, on a ship, because you can use inertial navigation, but it might be much more problem in aviation, and even short-term outages could there lead to misnavigation and problems. Then, as I mentioned already, the polar region is a very interesting region, especially also for these scintillation studies. So it's connected to changes in the solar wind and especially effective under atmospheric storms. The region is interesting because there's now much more possible. The sea ice is unfortunately is a reduction of sea ice, but on the other hand, it allows also much more traffic and even resource exploitation in this area. This attracted the interest of several economic sectors like oil, gas, mineral industry, fishery, forestry, and tourism. And especially space weather can occasionally cause complications in such activities. And this needs accurate and continuous service for navigation, communication, and environment monitoring. You need really precise navigation there. It's a difficult area. Space weather events are more frequent and at this high latitudes. This is another thing which you have to take into account. And this is also due to the topology of the Earth's geomagnetic field. And the dynamics with its high local and spatial variability and high latitude is not completely understood so far. So there's still research necessary to have proper modeling of this region. And also coordinated on continuous measurement of fast and short-lived sources of disturbance in this area, especially with trans-atmospheric connection between satellite and receiver is needed. And you see here, there are a lot of data for the equatorial region, even mid-latitude region. You have a lot of relevant traffic. You create a lot of data, but in the polar region, there's less or no data. And there was a German research vessel drifting with the ice for 1 year in the polar region. I will show on the next slide. Here you can see the economic routes, and now it's more and more possible also to get straight over the polar ice, maybe in future. So this is also important to address this region, which might be even more ship traffic in future. So we built up a measurement setup and a bit grabber device where we have a scintillation receiver, high-rate GNSS receiver, measuring scintillations. But with this bit grabber device, we could also store the signal directly from the antenna. And we could record scintillation data and replay scintillation data. And this allows you to test different receivers, because usually a receiver is a black box. You do not know how strong the receiver of different kind will be affected by such events. And here you can use the same event. You have recorded the data, and you can run a receiver through it and can test how your receiver will react on this kind of event. So this setup we have Polarstern and looked on scintillation. And the Polarstern is drifting with the ice for about 1 year, starting September. And this was for us a unique opportunity to install such a device, because there are no measurements in this region, and they are very important. And the data allowed to compare the performance of different receivers, and and even you can check identical conditions and develop new signal processing algorithms. And here are some first results from the data taken. So you see, you have scintillation events. We have a periodic triggering of those events. We get all this data. And here you see also the number of satellites affected and available. The thing is here that these bit grabber data they are terabytes, even for a short time. You really have to trigger them during the event. And we are still in the yeah, I would say on research, finding the right trigger for those. But these data are very helpful, and we are now analyzing the data. Unfortunately, I cannot yet show you the first results, but I think next time it will be there. Now we have analyzed more or less the triggering and the data, and we have the data available, and we are now investigating more in detail. And lastly, with my last slide, I like to make a little advertising. We have this Ionosphere Monitoring Prediction Center, IMPC, at DLR, impc.dlr.de. And there we show ionospheric products and services, pre-operational, where you can look at the actual state of the ionosphere and even get information on disturbed regions, areas, and this is will continuously extended and might also is already also used as an as a window for the outside to look at products, to test products, validate products, and it might be valuable for you from time to time to look what they are available and may some response in terms of what can be improved or what is already nice. So there's also the possibility to give some evaluation comments or some comments to the products. And we are already involved in big projects like the ESA SSA projects and as coordinator of Expert Service Center Ionosphere and also within the Global ICAO Space Weather Center Pegasus. And here we also provide data and information for GNSS user services. And with this, I hope I'm still in time. I'd like to thank for the attention and I am open for questions. Thank you.
Thank you, Jens, for this presentation. Any questions? We have 2 minutes for questions.
May I? Carlo
Yes,
speaking. Yes.
Quick question from Castra Veselin Vasilyev, if I may.
Okay.
Yes. So, what's your data or measurement of the effect of the human-made causes that may lead to ionosphere signal distortion compared to space weather, like let's say rocket launch or anything, any other events that may have similar physics disturbing the signal propagation and effect on the GNSS? What's the order of magnitude of difference of a solar-induced effect and human-made effect on that?
Usually the human introduced effects are smaller than, of course, if you have a big storm, you have much more gradients and changes in the ionosphere. Nevertheless, if you, for instance, you can forecast the ionosphere very well, climatology. In case you have a space weather event, that's much more difficult. However, if you have a real-time and the tech maps we provide are in 5-minute resolution. So you have real-time measurement and you subtract the climatology information on the ionosphere, then you only have the impact of additional effects from outside. This could be space weather events like ionospheric storms and gradients, but it could also be earthquakes after the earthquake typhoons, or it could also be some nuclear power, like Fukushima. There are also some papers showing that this was visible in the ionosphere. So if you have a really nice setup of reference networks to make precise tech maps and information, getting maybe also space-based observation data, radio occultation data, then you can have the tech maps or the ionosphere as a really nice detector for everything what's going on the sun, coming from the sun, but also coming from below. So it's can be used really as a perfect detector if you have enough data available. We have the problem, we use GNSS reference networks from ground stations, and so we do not have information over the mountain regions. We do not have information about the oceans. So there we need space-based measurements. And nowadays there are more and more such data from radio occultation measurements, topside measurements. So in future, there might be really a perfect ionospheric map, and then you get even these smaller events, maybe artificially caused by humans, you can see like rocket launches. Maybe that's possible.
Okay, thank you. Yes, I saw that we have another question.
May I?
Yes,
I was
yeah.
trying to yes,
before
just
Carlo, just before to give your question, please, Jens, stop sharing your presentation to see.
Okay.
Yes. Carlo?
Okay.
very simple question, because I'm aware that there are some also other. I'm referring to the last slide about the service center for space weather. That there is also other initiative on which probably of which you are aware, which is a ionospheric prediction service of the European Commission. Is there any connection with this initiative, which is ongoing, I think, for a lot of time?
Well, I would say we have contact to the people involved from different countries in the which have built up this IPS service for the GSR, and some of them are also in the Pegasus initiative. So we have contact. We are not directly involved. This was I think in GSR project, and we were also bidding, but we didn't run this project. So we were not involved in building up these IPS services.
It's running a service, yes. So also a service,
Yeah.
which is okay.
Yeah.
Thank you.
Okay, thank you, Jens. Any other questions? I don't see more questions about this presentation. Thank you very much. Of course, you will be here in the group, and we will continue discussion. Let's give the floor for one more presentation, or if you would like, you can make a 10 minutes break. Okay, I see some thumbs. 10 minutes break just for technical rearrangement, and we'll continue exactly at 5:30. Sorry, I don't know what is your time. Bulgarian time is 5:30. Central European time 16:30. Okay. Can you hear me? I think that we can continue with the next presenters. Okay, thank you, Dan. The next presenter is Yavor Shopov. Professor Yavor Shopov is a head of University Center for Space Research and Technologies in Sofia University, Bulgaria. He has a PhD in astrophysics and stellar physics. His main fields of research are related to application of satellites in applied and fundamental research, space and solar terrestrial physics, design and development of optical and spectral equipment for photographic registration in different regions of the spectrum. Professor Shopov is supervisor of the master program on aerospace engineering, small satellites, and co-supervisor of the master program on space research of Sofia University. Professor, I hope that you can hear me.
Yes, I'm here.
Okay, the screen is yours. You can share your screen and share your presentation. Or
yes, just a second.
Yes. See your presentation.
Yes, this is my presentation.
Now it's okay.
Regarding variations of the solar cycles and their impact on radio propagation.
Professor.
Yeah.
Is it possible just to put in the full mode?
Yes, just a second.
Thank you.
Okay.
The screen is yours.
Okay. So unlike the previous talk, I'm going to speak regarding the cyclic processes, not solar events, which also impact the ionization of the ionosphere, and in our case, we are going to focus on their impact on radio propagation. Now we studied variations of the solar cycles and their impact on radio propagation by real space periodogram analysis. And actually this new algorithm for periodogram analysis allows us to compare the intensity of the cycles, which is important in such studies. So we studied variations of the available proxy records of the solar ultraviolet irradiance, which is responsible for the ionization of the ionosphere, particularly F10.7 centimeter solar radio flux, Lyman alpha index, and a new EUV proxy, E10.7. We obtained significant variations of the solar ultraviolet irradiance with periods of 26.4 and 0.9 days, 216, 256, about 1 year, 585, 819 days, and 11.2 years. These cycles produce powerful long-term modulation of the radio propagation. And we attributed the 26.4 and 0.9 days cycles to the solar rotation, while this with duration from 341 to 372 days to cycle of the Earth's rotation. These cycles allow they are using for prediction of the solar modulation of the radio propagation. And in fact, solar wind produces a magnetic field called this interplanetary magnetic field, whose subtle influences reach the surface of the Earth. It is well established that the radio propagation depends strongly on the ionization of the ionosphere produced mainly by short-wave length solar emission, particularly by the short UV emission. That's why here we study periodicity of the short UV emission and F10.7 centimeter solar radio flux in order to estimate the periodicity of the radio propagation. As the source, Solar Radiation and Climate Experiment satellite mission demonstrated, far ultraviolet irradiance from the sun varies by as much as 10% during the sun's 27-day rotation, while the bright 121.6 nanometer hydrogen Lyman alpha emission may vary by as much as a factor of 2 during the 11-year solar cycle, dramatically affecting the energy input into the Earth's atmosphere. And several words regarding our experimental approach. We studied the periodicity of the extreme ultraviolet emission expressed by three indices: Lyman alpha index, F10.7 centimeter solar radio flux, and E10.7 proxy for the time period from 14th of February 1947 through May 31st, 2002. And all these proxies represent the short wavelength solar emission producing ionization of the ionosphere. But the most precise of all these indices is E10.7 proxy. Then we designed a special algorithm called real space periodogram analysis and relevant computer program code to compare quantitatively the intensities of all cycles presented in the study data. It plots the periodogramming coordinates of the real space, I mean cycle intensity versus period of the cycles in years or in days. We use it to study the periodicity of the short UV emission in order to estimate the periodicity of the radio propagation. Here are our results. In these two graphs, we've represented the intensity of the cycles in the time series of the Lyman alpha index of short wavelength solar UV emission during the studied period. And here we plot the intensity of the cycles in units photon flux in photons per second per square centimeter. And here we represent the same cycles in E10.7 extreme ultraviolet index. And here is given the 11-year solar cycle, which is in the same data. In fact, previous two cycles are just here on this graph. So their intensity is less than 10 times smaller than this of the 11 solar cycle. In fact, 11-year solar cycle is extremely powerful in short UV extreme UV radiation, which produce very strong 11-year solar cycle in the ionization of the ionosphere and in the radio propagation. And here we calculated the cycles which are contained in the well-known Wolf index of solar activity. And here you can see fine structure of the 11-year solar cycle, which is not exactly 11, but this is a bunch of cycles with duration from 7 to 17 years, and all these cycles have same origin, and this is just average situation, and basically the data which we use here don't have enough long duration in order to have satisfactory resolution to resolve the duration of this cycle. And here we have a plot of variations of the solar constant, which means the total solar emission, not only in the UV, but in the entire range, including visible and radio emission. And even solar constant have very distinct variations relating to the rotation of the sun. That's about 27 days, which have a different intensity, and the origin of this variation of the solar constant and solar emission in general are active regions on the sun like this. Here you can see two sunspots and surrounding much brighter regions of the sun, which basically produce the increasing of the solar radiation even in the visible region of the spectra. And here you can see cycles presented in this time series of the variation of the solar constant. And basically here you can see similar structure to that which we obtained from the short extreme UV emission, but variations of the solar constant are much smaller. So this kind of variations are produced from the same mechanism, but these are different expressions. What is interesting is that here this is not just one cycle related to the solar rotation, but we have again a group of cycles. The reason of this is that solar active regions are drifting on the surface of the sun. So solar rotation may be exactly 27 days, but active region may drift in the direction of solar rotation or in the opposite direction, and that's produced by rather complicated interactions of the magnetic field and hydrodynamics on the sun, which is called magnetohydrodynamics. And Anyway, this explains the type of behavior which we observed. And here we have a time series of the variations of the so-called solar constant during 35 years approximately. And again, sometimes we have very strong spikes in the solar constant, but we have also very powerful general trend with the 11-year solar cycle. And this is a picture, actually this is a magnetogram of the surface of the sun, which is taken exactly from the same time as this extreme ultraviolet image of the solar emission. And again, here we have a magnetogram, and here we have a distribution of the coronal holes on the sun. And basically, this material shows that we can really predict quite well solar impact on the radio propagation related to the rotation of the sun and rotation of the earth as well. But it's much harder to predict exactly the solar emission variations related to the 11.2 year solar cycle and of these solar cycles as well, which are not related to rotation, but are related to solar processes, which are not strictly periodic like solar rotations, but produced by solar magnetic field phenomena in general. And thank you for your attention.
Thank you. Thank you, Professor. Any questions? Any questions from the auditorium? I don't see any questions from the YouTube. Would you stop sharing, please, Professor, the screen?
Yes, just a second.
Okay, I saw one question on the previous lecture on the system for Jens. Jens, the question is, are these models that estimate in meters, for example, the errors made by the GNSS signal as a function of the input space weather parameters? Jens, are you here? Fortunately, Jens Berderman is not here. Okay, to our listener, we will send the question to Jens Berderman and he will answer in addition. Okay, thank you, Professor, for your presentation. If we don't have any questions from the WebEx, someone from the listener and watcher, of course, then we can go to the next presenters who are Lieutenant Kostadin Lazarov, who is next to me. I have a pleasure to be together with him. And yes, I know who is. And First Lieutenant Gutierrez Gwen. In short, if you can upload the presentation, please. In short, Gauthier Nguyen works as a space weather and artificial intelligence expert at the French Armament Agency. He just graduated from a PhD on the application of machine learning techniques to the automatic recognition of the signature of solar events from multiple spacecraft in situ measurements. And Lieutenant Kostadin Lazarov, I think that everybody knows Kostadin. He's working here in the center. In this presentation, they will provide a short overview of the existing artificial intellect techniques and present the opportunity they represent for the space weather community and in particular within our MSG group. Kostadin and Gwen, please, I'll give the floor and the screen. I give you everything just to see your presentation.
Thank you, sir. Thank you for the opportunity. Good day. As I was presented, my name is Kostadin Lazarov. I am a section head in our Ops Lab here in CMDR COE. And today, together with First Lieutenant Gwen, we are going to deliver a presentation about, is it here, the presentation? We are going to deliver a presentation about artificial intelligence in space weather modeling and possible task for our NMSG-187 related with searching of correlations between space weather parameters and processes and events on Earth. Just for a second to load the presentation. Yep. Next slide, please. So a few words as introduction about artificial intelligence. As you can see, the deep learning is part of machine learning, part of data science, and it's something very, very useful. Talking about artificial intelligence, a lot of people still believe that this is some kind of magic. And other people think that using specific technology, program, application, software, it's nothing artificial or intellectual behind it. Actually, personally, I believe that it's very powerful and useful instrument when we'd like to model something or to identify a specific process. Talking about data, next slide, please. This is one of the first step of the cycle when we try to model an object or process, let's say. Unfortunately, this step is time and effort consuming because for the most models which I try to build is valid the sentence garbage in, garbage out. There are some specific artificial intelligence technologies capable to deliver diamonds from the garbage, but the possibility and the chance is relevantly low. However, if we like to have a precise and accurate model, we have to prepare our data. In order to do that, we have to scale the data, to transform it in a specific format, and many other things. For example, if we'd like to cover specific range, of course, our input data should be applicable also. Next slide, please. The deep learning algorithms, there are a lot of them actually. On the slide are depicted just a few of them, and because some of them open source, there are huge variety actually of them. Most of them also we should say that they are applicable and relevant for specific task. They are effective and efficient for a specific task. Some of them are more general, like CNN, let's say, and could cover more tasks, more domains, and could be applied in different directions. Next slide, please. And about the APIs algorithms, probably most of you know something about Python, this relevantly new programming language. It's very useful when we're talking artificial intelligence development because, for example, it could work with very complex and sophisticated data types. They're combined in, they are stored actually in containers. We are talking about multidimensional vectors, for example. Same the situation with TensorFlow. The containers there is called tensors. So we have different languages, different APIs. Going back to Python, I have to say that it's comparing with C++, for example, the speed of Python is slow, and Python has advantages and disadvantages, and the application depends on our needs and requirements. So different APIs, and especially when we're talking about science and such kind of researches, for sure, the programming is not the first priority. We use what is most convenient for us. And now, because I'd like to stress the attention on the second and third part of our presentation, I give the floor to First Lieutenant Gwen to continue with the presentation. Gautier, the floor is yours.
All right. Thank you, Lieutenant Lazarov. So something that hasn't been mentioned yet is that artificial intelligence is now widely used in various domains. Well, I guess I learn you nothing here. But what is interesting is that is also a flourishing trend in space weather. And a reason that explains it is that we already have a large and ever-growing public space weather databases, whether they are sun images, plasma data measurements, geomagnetic indices measurements, or even ground-based magnetars data. And this flourishment is seen with the right panel that represents, as a function of the years, the number of scientific publications that concern both artificial intelligence and space weather. And we see a clear increase with time. So these techniques are particularly appreciated for their fast processing of input data and the ability they have to equal or even outperform existing state-of-the-art models. And so in the case of space weather, we are going to find various use cases. Next slide, please. Various use cases at every step of the sun-Earth chain. For example, a lot of these techniques are nowadays used to forecast the geomagnetic indices that give clues about the current geomagnetic activity. Next slide, please. Another use cases pretty interesting is that they are used to interpret sun images. And next slide, please. The last use case is their utilization for the classification and forecast of streaming in situ plasma measurements. So I will just go briefly on these three different use cases. So next slide, please. So concerning the forecast of geomagnetic indices, this is a problem that has seen its number of publication increase in the recent year with the utilization especially of recurrent neural network to forecast the value of numerous geomagnetic indices such as the KP, the IP, and the DST for those who are familiar with those indices. And we already had a presentation within our group about the application of AI techniques to the forecast of geomagnetic indices that has been given a couple of months ago. So currently those forecasts are made by the consideration of past indices measurements, and something that could be interesting to be done would be to improve those forecasts by considering additional data sources such as sun images or solar wind measurements. Next slide, please. So concerning the interpretation of sun images, we also have use cases of, in particular, convolutional neural network that are usually used for object detection, applied to the detection of sunspots and the forecast of solar flares. So this is the example you have with the left and the middle panel. And on the right panel, you also have example of utilization of those neural network to estimate the arrival time of coronal mass ejection to Earth. Next slide, please. And concerning the last panel, something that is often done is considering the data of the solar wind monitor that are usually located at the L1 Lagrange points, so just right in front of the Earth, and that permanently measure the upcoming solar winds. And one classical problem now in AI applied to space weather consists in finding a way to perfectly classify the different types of solar data that arrive on Earth. So this is what is represented here, where you have on the different panel the prediction made by one different algorithm with this color code that represents different types of solar wind classification. So if you go on the next slide. So this is something we also have been doing in France, but we stick to the main regions of Earth. So this is a project that we have ongoing in a laboratory in Paris, where you have on the top panel a measurement made by the Themis spacecraft. And on the bottom panel, you have the region, well, you have this this curve that indicates the region in the near-Earth environment in which the measuring spacecraft is actually located. So the magnetosphere, the magnetosheath, and the solar wind. And we have trained a machine learning algorithm to actually classify those regions from those streaming in-situ data. And you have its prediction represented by the black curve, and you see that it almost sticks to the ground truth, showing its actual efficiency. So another interesting thing that can be done is, well, here I have shown just classification example, but we also have use cases of the development of techniques that are able to detect the beginning and the ending time of specific events such as solar events. So if you go on the next slide, this is also a project that has been developed in France, actually, where the idea was to develop an automatic detection method of interplanetary coronal mass ejections. So for those who are not familiar with this, coronal mass ejections are giant plasma bubbles that are emitted at the sun's surface and that propagate in the interplanetary medium. And those events, well, are quite interesting because they are considered as the most geo-effective solar events. And they can be recognized from in-situ data measurement from so this is what is shown on the right panel, from an enhanced magnetic field on the first panel, and this low plasma beta parameter in the second panel. So the main problem we have is that this signature, if you go on the next slide, is actually not always this obvious, and this is why their manual recognition in data is not always this obvious, and we are interested in automating it. So if we go on the next slide now, so this is how we made it in our lab in Paris. We built this artificial proxy that appears in the bottom panel that indicate the presence or not in data of a coronal mass ejection. And we trained an ensemble of convolutional neural network to reproduce this pattern from the streaming in situ data we have on the 4 first panels. And so if you go on the next slide, this is how it looks on this very simple example. But if we go on the next slide now, we see that on 3 months of data, we also have an interesting reliability of these techniques that also comes with an interesting visual indicator that is currently being implemented on an under development visualization tool. So this method sees a lot of events and makes a few mistakes and allows the reproducible generation of as exhaustive as possible events catalog. And this method is actually accessible online at the link you have on the slides. So we've seen various use cases of AI in space weather, but this has been limited to solar events and to their eventual forecast. And we realize that for now, there are very few use cases of AI to estimate the potential impact those solar events could have on Earth. And so this is why we are going to move on to the third part, and I will give the talk to Lieutenant Lazarov again on what could possibly be done within the frame of our group.
Thank you, Gauthier. Now I'd like to continue with this possible additional task which we would like to propose to the group, to NMSG-187. It's about searching of correlation between space weather parameters and processes and events on Earth. We'd like to make such comprehensive research and analysis. Why? Because this magnetic shield actually is not perfect. Part of the space weather impact goes through it, and parts of the energy actually is transformed through the shield. So we can expect to have specific impact in 3 different domains on Earth, or we are interested actually in 3 different domains. The impact of space weather over the society, technology, and environment. And we'd like to search, as I said, for correlations between space weather and these 3 different domains. Next slide, please. So in order to do that, again, as I said in the beginning, we have to do one very, sometimes, let's say, sometimes a boring task. I mean, to prepare the necessary data. On the left side, you can see data relevant to the space weather and elaborating its parameters. On the right side, there are a lot of boxes. Actually, there were more, but because of useful comment from Gauthier, for example, natural data contains meteorological data, data about animals and plants, flora and fauna, data about physical processes on Earth, like disasters. Very specific data is concerning societies, stock exchange data. Another very broad database is national statistic data, etc., etc. So we are going to make different test cases. So we are going to use the same left side data. I mean, elaborating the parameters of the space weather, and we'll have a specific use case with specific data taken from the right side databases in order to search for these correlations between space weather parameters and processes on Earth. Next slide, please. Because both of us, me and Gauthier, we agreed that supervised training is the artificial intelligence technique which is probably most applicable in our case. On the slide is depicted the loss function, and if we're able to achieve such a value of it, it will be great because it means that we already found such correlations. So on the right side, you can see that the value of the loss function depends also on the data set previously mentioned. So we have also some proposals in this example of the technical solution about the usage of specific algorithm. There is mentioned convolutional neural network and long short-term memory network, PyTorch as API, and of course the usage of specific computational power. That is for me, and I'd like to have the opportunity to discuss later with the group about this additional task, and I'd like to give the floor again to Gautier in order to make some comments, especially on the previous slide. Gautier, back to you.
Yes, thank you very much. Well, just the last word to finish the presentation. I don't know if you have mentioned it. I just had a problem with my microphone. But in addition to those correlation, well, actually what is really interesting is that if we actually find some of those correlation, we can go even in a longer term and think about the development of forecasting tool and see it with this forecasting vision. And I think this is my last comment, and I thank you for your attention, and I'd be glad to answer any questions.
Thank you very much, Colonel Lazarov and First Lieutenant Gautier. Actually, can I call you just Kostadin and Nguyen? It's more easy for me. Any questions? I think that is very interesting proposal from our participants to our group. I think that it deserves to take attention of their proposal, and even before I don't see any hand rise up, but I have some thoughts. For example, if someone has data of something, for example, let's take disaster or flooding in some area. Very simple, what is related to my work. And you have a behavior of the space weather with artificial. Then if I give you this data of the disasters, and I'm interested to see if the space weather related to disasters in this area, you can see the correlation between the space weather and for example, this flooding in this area. Or if there is no correlation, of course, you can say, yes, this is a flooding. Maybe you have a flooding sequentially on 5 or 10 years, it doesn't matter, but that is not related with the space weather. Mm-hmm. If I can generalize this idea, am I understand correct?
Absolutely, sir. So, as Gautier said, if we are able to find such correlations, we will not be able only to predict such events in future, but also to understand them in more comprehensive way. Of course, when we feed the algorithm trying to develop our model, there are some indicators which we can see, and when we feed with additional set of data, the model will be improved or the accuracy will be decreased. So with each additional set, we will see we will be able to tell, yes, there is a correlation between, because when we feed additional data, the model is improved, or no, there is not correlations because when we feed the model, actually the algorithm training the model, the model, the parameters actually, and the overall accuracy is decreased. So the short answer is yes. We will be able.
Actually, yes. Sorry for interruption. My second question was that do you think that someone else already not started this one? And I will give the floor to the I think from Noah. Yes.
There are some researches, especially when we're talking about the impact over the technology, because it's visible, but there is a significant gap in, especially in social processes and events, and when we're talking about the environment. So I think that if we're able to start such research, especially if we build the necessary interface for it, it will be very useful for future when somebody, as you said it as an example, sir, when somebody is ready with additional set of data just to feed the algorithm and to see what is the result.
Yes, thank you very much. I would like to give the floor on the raised hand. Please present yourself.
Yeah, thank you. I'm Sue Fan from NOAA Space Weather Prediction Center in the US. So it's a very exciting study, and then your result is very promising. The only thing I have, and I want to comment on, is we really don't have enough space weather event in the past two solar cycles. So you got to be really careful when we overpromise in terms of the space weather impact on a lot of, just because we don't have enough data to capture, especially the extreme event can be extremely impossible to be captured by the machine learning algorithm. So just one of the comments, so that we are not overexcited about that opportunity, but just be cautious. Thank you.
Also, it's very interesting what they presented, and I think that there is a future. For me, the challenges is not in the artificial intellect in your case. The challenges maybe is more to find appropriate database about the space weather. Maybe for other data we can find it, but maybe for space weather. But that's why you are here and we are here, and we can see who, what have. And that's the idea actually of NMSG-187, to find all data and all kind of models and etc. what is on the market. Okay, yes, please.
Maybe Gautier would like to comment also.
Yes, actually, this is indeed one of the main problem we have. I agree with you. We still lack of extreme events, as you just called them. And well, at first, I'd say that this is something that is called to be improved with time. Well, those algorithms are well known to improve their performances with the increase of the amount of data they have at their disposal. So we can expect that the more we advance in time, the more we have recorded events, and then the more it gets performance. One other thing we could think about would stand in, indeed, apply some data augmentation techniques to see if it improved the performances of those algorithms. But I think we're a bit far from this right now in our reflection concerning those projects. But this is definitely something we have in mind.
Yeah, thank you. Any other comments or questions? Dan, what do you think about this proposal?
So I think it bears a lot of great interest. I'm actually pretty interested in seeing where we could go forward with it.
I couldn't understand you very well.
Can you hear me now? I think this there's great interest in this, and I think we should look at it in a little bit more detail.
Okay. Okay. Yes, definitely. That is my idea also, and of course, thank you very much for both of you for your presentation. And I would like to continue with the next one. The next presenter, according this schedule, could you upload the presentation, please? Just not to make your. Yes. Mr. Supriya Chakrabarti. Can you hear us?
Yes, I can. Thank you.
Yep. Actually, you are already. We are very well known with you from the previous meeting. Now it's your time. You are director of the Center for Space Science and Technology, University of Massachusetts, Lowell. And you can see on the slide what is the idea of your presenting. Please, the screen is yours. Share your screen and you can start presentation.
Well, I'm
50 minutes yours. You have your 50 minutes.
I'm very happy to be invited back, and thank you very much. So I'm going to describe a small instrument that we are designing and about to fly on a CubeSat. And this is all done by undergraduate student at our university. They developed everything. And so this particular instrument that we're going to talk about will not fly on this CubeSat, but it fits within a CubeSat. With that, let me give you a little background on how we came to this. A long time ago, I came across this paper from some Indian colleagues who were trying to predict equatorial spread F by looking at airglow emissions during the daytime. And those of you who are familiar with these emissions, you know that these are subvisual emissions. They are seen in the night sky as well as in the aurora. But they were trying to do it during the daytime when the sun is up, and they were trying to do about 2 in the afternoon local time. And the idea is their prediction, their goal was if they could observe it and see certain characteristics, they could then tell that whether there will be any equatorial spread F in post-sunset time. At that time, I grew up in the ultraviolet world. We built instruments and flown on satellites. Primarily, some of the things that Dr. Berderman talked about, the 304 or angstrom or 30 nanometer emissions, again in the plasmaspheres and others. We have built instruments to do airglow work from STP 78-1 satellite. And then also at our center, we have a network of digisuns, the GIRO. But this instrument, because we do optical instrumentation, this caught my eye. So we, over the next 20 years, we have developed various instrumentation, and we have developed this tool that can measure not just one emission in here, but a number of these emissions. And one of the recent results of our work was in the JASTP, where we have now developed several versions of this instrument, and we are using it for different applications. So once we have done this, our thought was, could we make it a smaller? This is a desktop-sized instrument, but we wanted to see if it could be made smaller and be applied for CubeSats, since those are becoming more used. So there was a coincidence that happened at that time. The Google Lunar X Prize work was going on, and one of the contenders asked us to see if we could build an instrument that could fit within a 1U size of a CubeSat. So that's the instrument that I'll describe to you. The idea is very simple, just like any other camera. In this particular case, light enters through this little cyan color pupil, which is shown here. And then because it's a CubeSat format, we had to bend this, fold the optics, and image on a CCD camera. And because we are given very short time, we wanted to see if we could put something like this together using off-the-shelf components. The key to this instrument is this little purple thing. It's a mosaic of filters, which sort of looks like this. And these are very carefully chosen to select some specific emissions. And so in this particular case, we had a we chose the filters to do sodium and potassium because those are very common in the lunar atmosphere. So the wavelengths that we chose are, this is the sodium emission, 589, one of the two doublet prominent lines that you see, and this is the potassium line. We've designed and built it. These are the performances of the filtered imager. And here is one of the first images. We were sitting in this building, this L-shaped building. You might be able to see this line. And we're looking towards this building. Our university is in an old mill town. So there are all these smokestacks and the buildings. In this case, you can see that these are nighttime. So the lights are on in the windows. And so this is something we built and tested it. And we also took the same instrument and put it on a NASA high altitude balloon. So this little thing in there is the balloon. As you can see in here, this is 10 centimeter by 10 centimeter, and the height is even smaller, about 7 centimeters. So we were given these sort of parameters, and our instrument looks like this. The key thing to know, and on the right are the data from the balloon during the flight. This is about 3,000 feet height, and this is a little higher. The key thing to note here are this is completely reconfigurable by just simply changing these filters. It's almost like the old European stained glass windows. Those are the filters. You could put it in any configuration you want. So it's highly flexible, very easily changed. So this is a balloon that had a 60 centimeter diameter mirror in here. So that's for an astrophysical application, but we flew this as a test. And we flew and we saw the data, and here you can sort of see right before we start, these are the, again, same 4 bands. And these are images taken, each snapshot is roughly about a millisecond in the daytime. And you'll notice that, some people will come, there's a truck that went by. This is, it hasn't launched yet. Here are some people. And very soon you will see it launches. There it is, it launched. And we collected data in those bands simultaneously. And the idea is in a push broom imaging sense, if your field of view move over a feature, you can take the image in all colors. So the next step for our instrument is to compare it with those bigger instruments that we talked about. This is again an instrument that can see 6 atmospheric emission features, red, green, blue, etc., and H alpha, H beta. And we want to put them side by side to compare how this instrument, the little instrument, compares with the more larger, more capable instrument. This is an imaging spectrograph at very high spectral resolution. So what we decided to do was we went back and looked at what are some key emission features in the Earth's atmosphere. And there are these emissions that are highlighted. This is the green line, that's the red line. This is 77, 74. It's an O+ emission features. There are some molecular nitrogen features here. So we picked some of those and now got a different set of mosaic. So this is the photograph of that. There are now, instead of 4, we now have 8 such filters for upper atmospheric. In addition, at the bottom, we also put in some Landsat filters to show how well it could work for conventional ground remote sensing. So this has been now put into the instrument, and we are now testing and calibrating it, and it's going to fly sometime this September, along with the other big instrument. So that's the update on this instrument. And as you can see, we have already established from ground-based air glow measurements, we can, there are indications that you might be able to say something about the development or spread F or some other features that in the air glow that you may want to do. And in here, we're trying to show that even a small package in a CubeSat 1U package, you could put a very powerful sensors that could be used in other applications. And the only thing that restricts us is the sensitivity of the detector. We use a CCD or CMOS detector, so that's why we're restricted to the visible, but we have other design that can work in the ultraviolet or other wavelength region. So to summarize, we have now a very versatile instrument for different kind of applications, and it can be, if you stick to the visible, it can be very quickly adapted for different applications. The first design, as I mentioned, was chosen for lunar atmosphere. Now we are going to do the test flight of the upper atmosphere. And after this flight, we will know that certainly it is suitable for balloon type environment, and we know how to ruggedize it for various spaceflight application. So with that, I wanted to thank you for your attention, and I look forward to answering questions.
Thank you, Mr. Chakrabarty. Any questions? Do we have a question from YouTube or from the? No. Okay, from the WebEx participants. Do you have any questions from to the Mr. Chakrabarty? It's perfect for you. That means that everybody understands everything or nothing. I'm sure that everybody understands everything. And thank you very much, Mr. Chakrabarty. We will continue with this one. I saw something similar with the idea of using of data, and I think that together with our young specialists, I'm sure that they will turn to you with help, how to help them about the artificial intellect and their new project maybe. Thank you very much. Let's continue with the next presentation. It's degraded environments by extreme space weather by Professor Mauro Messerotti. He's a researcher at INAF Trieste and professor at Trieste University Physics Department, space weather specialist and co-founder, astrophysics researcher and professor, as I mentioned, in University in Trieste. Professor Messerotti, can you hear us?
Yes, thank you very much. Now I share my desktop.
Yes, please.
Hopefully it should work. Can you see it?
Everything is perfect and the floor is yours.
Okay, thank you very much. Thank you for having invited me, also giving me this time slot for giving this presentation. I apologize in advance with the audience because this presentation is very dense. In fact, I wanted to give you a comprehensive view of the work that we have been carrying out in the framework of STO just in the last years, and also some conceptual schemes that show a sort of, say, pipeline for making a system analysis. Then I will be a little bit pessimist when I will give the summary and the conclusions. Many of you will not agree with my conclusions, but my motto is that a pessimist is a well-informed optimist, and you will see, I mean, when I will elaborate on that. So I will just speak about what we do mean by degraded theater environments. All my presentation is in the perspective of military operations mainly. Then I will speak about extreme space weather events in the military framework. A very important point is the impact, severity, and risk assessment and space weather services for military operations. This was addressed by previous speakers. Then I try to specify a list of information requirements for space weather, again in the framework of military operations, And this is the most controversial point that I will elaborate, that typically will horrify the audience. What is, in my analysis, according to my view, the state-of-the-art knowledge in space weather science and operations. So let us start with the degraded theater environments. I will not go explaining all the details of many slides, because otherwise I will not be in time in the 20 minutes that we have. So just to consider at the highest level of abstraction what we do mean by theater environments and the sources of perturbation. All the military operations occur in the theater, and the theater is located in space, in the atmosphere, on or in the water, or in the ground. And of course, there are perturbations that affect such kind of environments. We will see in more analytical way as much as possible, provided that I will have some time. But the natural perturbations are space weather, near Earth objects, of course, and weather. And regarding then the man-made perturbations, we have space debris and malicious actions by the adversary. So we can prepare a concept map. I will not go into all the details, but just to say that if we consider such environments, space, air, land, and water, they are characterized by a physical state. This physical state can be perturbed. For example, can depend this by intrinsic sources of degradation of natural origin, like, for example, geography, orography, and so on, or extrinsic sources of natural origin, like weather, as said, or space weather. Or we can have, for example, a perturbation due to man-made origin locally, for example, the layout of buildings in the theater, or the mission layout itself, which is very important to take into account. And of course, the degradation level causes a deviation from the ideal operational conditions set by the mission requirements, that is the goals of the missions. Then, of course, for extrinsic sources, we mean sources of man-made origin like mission operations, adversary actions, and so on. So it is very important to make an adequate mission planning, take into account risk analysis. So we have to understand what are the services on which the mission is based. For example, landcom, land networking, land video conferencing, then navigation or satellite communications, satellite networking, satellite video conferencing, satellite navigations. And to consider that, we have to analyze for a specific mission, mission A, for example, that these can be based on a set of services that are characterized by a criticality, no criticality or limited criticality or high criticality, and availability of the services. None, limited, high availability, and then we have to carry out a cross analysis to understand and quantify the mission feasibility and the success probability. This is a complex operational scenario that I have developed for some exercises in the framework of some lecture series where all or many of the different ingredients are here represented, the satellite communication and observations, the UAV, of course, the different communication links, but we have also on the ground the battle tank, the troops, the movable commanders, submarines in the water, ships, and the main operating base. Everything is referring to the NATO wide area network. So we see that this is a complex scenario in the theater. And this requires a complex monitoring scenario. Here you can see one of the dashboards that I have conceived in the exercises where you can get just at a bird's view all the perturbations that can affect your systems. And we go here, for example, considering the electromagnetic pulses or the run pressures of the solar wind or geomagnetic storms, or NEO, because also NEO, it's a rare, say, event, but it can occur. The space debris as well, the single event upsets, and so on and so on. So one can evaluate using such kind of dashboard all the different, say, perturbations of a natural or man-made origin. You see that here we have JAM, cyber, laser, EMP, and denial of service, and so on and so on. So what are the needs, the operational needs in the military framework to cope with the degraded theater environment? So first of all, global monitoring for a comprehensive coverage and degradation assessment, local monitoring for specific degradation sources, both natural and man-made, reliable and robust nowcasting and forecasting system that is issuing understandable warning and alert messages, multi-level education for awareness rising, and multi-level training for mitigation preparedness. Oh, sorry, something went wrong with the navigation, but I will just resume immediately. Now let us go to the extreme space weather events and their impacts on military operations. First of all, what are extreme space weather events? We have problems with the definition, and we have problems in defining exactly what are the impacts in military applications. Various definitions of extreme space weather events you can find in the literature or used by different agencies. This is creating semantic ambiguity. The relevance of extreme space weather events to military operations depends on events' nature and impact severity. And a clear definition and an effective assessment are desirable to achieve the needed awareness and preparedness. How do we define an extreme space weather event? First of all, a consistent definition is to consider that an extreme space weather event is in reality or actually a cascade of component events that usually are originated by the solar weather characterized by the solar activity level. Such component events are non-linearly coupled from the physical point of view and result in energy transfer to geospace and planetary environments. Let's consider a correct approach to the definition. It has to be based on a semantics which is consistent, both physically and phenomenologically, the energetics of the component events cascade, and the severity of impacts. You can find very many varied and misleading references that define an extreme solar weather, space weather event like a solar flare or a series of solar flares, or I go briefly, geomagnetic storms or radio blackout or relevant impacts on technological and or biological system, or the whole solar terrestrial events cascade. This is a simplistic and incorrect approach that can be source of ambiguity, especially if I have to use them in the military framework. So all the events observed and the relevant impacts have to be considered to fully characterize the complex event to avoid just a partial identification of causes and effects. The severity of both phenomenology and impacts can be quantized according to thresholds, which, when exceeded, define the complex event as extreme. But there is a caveat, because a space weather event can be extreme under some global or local circumstances, depending on the framework of the affected system and their role in specific applications, so that it is impossible to formulate an absolute definition for a space weather event to be classified as extreme, because such a character is intrinsically relative. So we have a cascade of physical processes. I have no time to elaborate that. You have the presentation. The interested people can then read offline, and then we can discuss offline. But we have typically solar weather events, solar flares, for example, interplanetary weather events, coronal mass ejections, geospace weather events, the interaction of CABs with the magnetosphere, magnetospheric weather events like geomagnetic storms, ionospheric weather events like total electron content variations, scintillation, and so on, and geospheric weather events on the ground, like the geomagnetically induced currents. So you see that the cascade is quite complex. And then one could consider solar weather events starting from the topology of an active region on the sun. Then the acceleration of a coronal mass ejection that propagates into the interplanetary medium like an interplanetary coronal mass ejection. And then upon the interaction with the magnetosphere, we have an energy transfer and we get an unstable configuration potential that depends on the compression amount of the magnetosphere, its variation. So this is triggering a magnetospheric geomagnetic storm, or say a substorm. And we have some descriptors like the KP and DST indices, and the relaxation can originate geomagnetically induced currents, but we need a description by intensity and geography, of course. Okay, again, I had a problem with the navigation. I fixed that just before, but apparently there is a problem. Sorry for that. And so what are the impact, severity, and risk assessment that we can carry out? First of all, we have to define specific thresholds. So there are plenty of descriptors, indices, proxies, and so on. But we have to define thresholds. When the thresholds are just overcome, then this indicates that we are in a critical condition or extreme condition. For example, for enhanced solar energetic particle fluence, radio scintillation, radio blackouts, geomagnetic induced currents. And so if one or more of such critical thresholds are exceeded, then the complex cascade of events can be classified as an extreme space weather event. What about the relevance for military operations? In a military framework, an extreme space weather event can cause the unavailability of many services on which operations rely on. For example, communications. We have seen before in the simulated theater scenario how this is dependent on radio communications, networking, and so on. Is a mission critical factor as it can completely jeopardize specific operations despite of the availability of backup mitigation techniques that not always and for all services are available. Hence, we need actionable forecasts, nowcasts, and prompt warnings just to cope in the military operations with this kind of situation. And we can prepare some, for example, management tables in the military framework that we have, as an example, developed in the SCI 229 just research task group, where you have an event with its probability, low, medium, high, very high, and the relevance of impact for mission. The mission can be unaffected, important, essential, or critical if really we have a great impact. Of course, such events are affecting the whole chain of the space systems. For example, here are mentioned, but I will not enter into the details, some effects of the just photon outbursts and solar energetic particles on satellite segment subsystems, but similarly we have effects on the subsystems that are in the ground system, because of course we have electromagnetic radiation outburst, ionospheric weather, communication subsystem, geomagnetic induced currents, power subsystems, and so on. Just in the report of the STO SCI 229, you find all these kind of schemes. What are the services that we have at disposal for military operations? I try to make a critical review, and I know that this does not make very happy many people. Anyway, monitoring and warning services for MIL. We have governmental, institutional public services, non-public services, Department of Defense customized public services upon some agreements and so on, and the classified services that are DoD proprietary, and so these are not open to the public, but just to the MIL, of course, community. What are the requirements from the point of view of the information about space weather that we need to cope with appropriately with the military operations? First of all, the information must be target user dependent, must be prompt, must be essential, not redundant, must be comprehensive, not limited, must be standard, following some standards, some metrics, must be user-friendly, must be relevant to global effects, but also to regional effects that are very important on the theater. And with alerts and warnings that are provided with nowcast and forecast. And there are specific requirements regarding this set of information on space weather. They must be tailored according to the expertise of the user. If he, she is an operator, a specialist, a soldier, they must be adequately timed without redundancy that can be misleading. I don't want to know all the physics of the propagation of a CME, but just to know if there will be a perturbation in the magnetic field. Covering the relevant phenomenology and impacts, compliant with an agreed messaging standard, easy to understand to the non-specialist or to the soldier, descriptive of the globality of phenomena and impacts, descriptive of the locality of phenomena and impacts, and constituted by alert and warning messages that contain nowcasts and forecasts, as said. So the goal of the requirement is just to be able to cope with extreme space weather events in any military situation, such as, for example, support of civilians in natural hazards and peacekeeping activities, because the proper messaging is the basis for any coordinated and effective response as prescribed by awareness and preparedness about the phenomenology, its impacts, and the mitigation techniques. This is a possible scheme about monitoring, modeling, and forecasting. I don't have time to go through, but you start from the phenomenology on the sun, and you come with a space weather message that can be automatically generated, but very often it is hybridly generated when also you have a human forecaster that is needed to really interpret what is occurring in the different environments. In the framework of the NATO SCI 229, we have developed some, say, prototype of web-based space system status monitor. You can see to the left, in the left panel, just the home page where you have the different domains, space, ground, and user. And then clicking on the different icons, you get the relevant information. For example, here, if you click just on the space subsystem, you get the different messages regarding what is critical at that time. There is no warfare attack, but there are natural perturbations affecting your space system segment. And now I come at the end, and this is the most controversial part. This is the state-of-the-art knowledge in space weather science and operations. Just take into account that I have been involved in that, say, for 40 years. In fact, I will go just to retirement in August this year, when space weather did not exist, but there were solar telestial relations, cosmic physics, and so on. So I have a long say, experience in that. And just taking this kind of experience and trying to convert this into a scheme, here I could spend just many hours in describing this scheme. This is showing the different perturbations that originate in the solar interior, at the solar surface, and in the solar atmosphere, that are just propagating through the solar wind and the interplanetary medium, and then comes just to the outer radiation belt in the magnetosphere, the inner radiation belt, and generating the South Atlantic anomaly. The plasmasphere and the ionosphere, of course, the fast solar wind streams and solar energetic particles, and then, of course, also the magnetosphere, which is perturbed at different levels. So we have to consider the photon, of course, component. These are particle components. Magnetized plasmoid is a coronal mass ejection, but we have gamma, X, extreme UV, and radio photons that are creating, we heard also from the previous speakers, different perturbations. And this is the most controversial table. I know that you will, perhaps not all of you, will hate me, but this is the actual capability that you can derive just from the different operations, from the different agencies trying to make forecasting of space weather, and from the literature. So here I try to consider for solar weather what we can nowcast and what we can forecast. What we ideally would like to. We would like to predict the emergence of an active region. We can make only nowcasting. We have no means to make any forecasting. Don't misinterpret what I am saying, because I have been also working with artificial intelligence and with machine learning and deep learning. But this is a defeat of physics in this sense, that when we rely on machine and deep learning, this means that we don't have a consistent and comprehensive set of physical models to properly describe the time evolution of the different perturbations. This is the real situation regarding solar activity and the Sun-Earth coupling. So we are unable to predict the active region emergence, and we are unable to predict the magnetic evolution of an active region. Yes, there are many precursors and indicators and so on, but the confidence level is still not satisfactory. Similarly, the prediction of flaring, but not only of flaring, but also with the topology and the dynamics of the flaring region. There are some, say, shy attempts to do that using machine learning and deep learning, but as it was stressed before, we don't have a number of events sufficient to have a good populated set of data for having the training of the convolutional neural network. Similarly, we are unable to predict photon outbursts, but not only the photon outburst occurrence, but also the spectrum and spectral peak energy. Similarly, the prediction of CME generation, but we also need the mass, the topology, the speed, the direction, and the magnetic field, the flux rope. Also for that, there are some methods based on artificial intelligence that are helping, but are not the solution at this time. So we have the CME time of arrival that can be predicted because the CME is just propagating quite slowly with respect, for example, to a bunch of photons. But still we have difficulties in estimating the impact strength of the CME. Will this, upon interaction with the magnetosphere, trigger a substorm or just a geomagnetic storm? This we are unable to do. And similarly for the solar energetic particles acceleration, because we need to know also the species, the differential energy spectrum, the fluence, the rigidity, and so on. So just we can do some forecasting on the time arrival of solar energetic particles, but we are very limited in this context. Okay, sorry, let me go to the conclusions and just this is the summary slide. So I have shown you what is a sort of pessimistic but realistic say. So we can conclude in this way. We can say that a correct definition for extreme space weather events in military applications is relative to the operational framework. It cannot be provided a priori. Military mission analysis is very important and must be based on space weather impact severity analysis. And to be actionable, space weather information for military applications must be provided. That is based on specific requirements according to multi-level messaging. That depends on the target. What is the target? Can be an operator, can be just a commanding officer, can be just a soldier of the troop. The knowledge we have, and this was said, in fact, on extreme space weather events is quite limited. And to date, the capability of space weather forecasting is quite limited. And for the majority of them, we can only carry out nowcasting. And extreme space weather events have been a real threat for military mission success, so must be taken into account. is the end of my talk. Sorry for being very long and apologize for the high density of the presentation, but I hope that at least I gave you a bare idea of what we have done in the last years, also in the framework of STO, SCO.
Thank you. Thank you, Professor. Actually, the picture is quite different here because we are face to face. Actually, they just disappear from the call. I'm joking, of course. They are not sleeping. Okay, I thank you very much for this presentation. And now we understood that. Actually, I understood. Maybe the other know more than me. That we already have a definition for extreme space weather events, but cannot be so exact as a definition because with a lot of probability. But do you have a database for extreme space weather events?
Database exists, but they are quite limited indeed. So you can learn something from great space storms, great geomagnetic storms, effects on the GNSS and so on. But the different samples are with a very limited population. That's the point. So it is difficult also to extract what should be the characterizing parameters. That's the main point that would help us in modeling and in forecasting. Also, let me make a short comment. It was said by Colonel Galton in the introduction. Often there is a sort of mixing or say misinterpretation regarding the modeling and the models. He pointed out, but I would like to focus more on that concept, that a science model is far from being an operational model. I can make a beautiful model for a category of flares, but I need to test it because it needs at least 10 to 20 years to be standardized, to be verified, and to be, say, approved according to specific metrics that now in space weather were set up. Otherwise, it cannot be used, my model, even if scientifically nice, for making predictions, because otherwise the predictions would not be really significant.
Thank you, Professor. Actually, the question was, do you have a data? Nothing else. And I think that now the Gutierrez and Konstantin Lazarov can contact with you and to explain them all this information, what you started. I see that we have other participants with questions to you. Is this one? Sorry, I cannot read it. Angela, I think.
Yes, hello. Hello from Edinburgh.
Professor, could you stop sharing, please, just to see the participants?
Oh, dear.
This is what I was.
On the orange, on the left, it's stop sharing button. Yes, thank you. And Angela?
Hello, Angela Matisse from Edinburgh Think Tank Maths. First of all, I must say, not falling asleep at all. Absolutely fascinating. I hope you're not going to retire your mind, your learning, your wisdom, because you might have spent 30, 40 years, but I think we're starting to need your knowledge and your wisdom now and in the future. So that's my first thing. And the other thing is, another principle that I think we all will agree to is that consensus does not guarantee the vital progress that humanity needs to make. These are some very fundamental principles of science and observation and learning. And very often it's from those interactions of viewpoints of view which produce the most fruitful discoveries and progress for humanity. Some general statements from me, just simply to I think just to give you an idea of the kind of thinking you have stimulated in your presentation. But I have a specific, and I put this to you. So our company, Think Tank Maths, we're we work not just in the space environment, but in the subsurface environment, so in geophysics. And one of the issues, and it's always this AI, what can you do with data? And I know there's a question here about do we have enough examples in order, cases to study, which will give us the data. That's I agree with the person who suggested this. And I think everyone's agreeing. But I think even in itself, if we rely too much on data science, I mean, data science is very powerful and we should not negate it. But on the other hand, what we see in geophysics, if you give, for example, if we want to understand, and please all bear with me, I would like debate, and unfortunately this dreadful medium of not being in the room together and to continue conversations is very limiting. But for example, if we're looking at a big place, a big area that will help humanity, carbon capture under sequestration, there are many people, there are lots and lots of data that humans have generated from this quite complex environment. And we're talking about the observation and analysis of complex environments and trying to predict, I think humanity, these are our challenges that face us. And when you come at it from a data science perspective, even if you're an extremely talented creator of AI and algorithms, what is needed, and we see this in this domain of understanding the dynamics of the subsurface of the Earth, is also you need to take into account the geophysics, so the physics and the chemistry, which then and the models that you draw from there, in order to keep a watchful eye on the assumptions and the simplifications you might make if you're looking to analyze using very powerful methods of artificial intelligence. I'd ask you to comment on what I'm saying in the space domain. I mean, it's certainly something that our company is also, we're very involved with the space domain awareness, space traffic management, trying to understand, and that's why we participate in this fantastic grouping of people in NATO. So this understanding of a kind of hybrid approach, where you're looking, yes, for data science, you're looking for mathematics, you're looking for physics, and you're looking for whatever else understanding of science that we try to bring together to give us a good result in this. Forgive me for taking so long, but as I say, it's a frustration and an excitement as to what you said. So I would pass that to you. Could you comment? Is what I'm suggesting part of perhaps would be something we need to take into account as we define what we would look at in this workshop? Over.
Oh, well, you really emphasized a very important point. That is the approach that is more, say, more useful in coping with such complex systems, and both the Earth and, of course, the atmosphere and the Sun are really complex systems in the physical sense. But we cannot just consider the mathematics of neural networks. We have to use also the physics that we know to optimize the mathematics. For example, a misconcept is that I remember at the former times, the artificial neural networks are black boxes. That's not true. It is not a black box that you feed with data and you get the results. But skilled mathematicians can derive models, mathematical models out of a neural network, at least the former generation neural networks. Now for the deep learning ones, it's more difficult because you have an hyperspace of parameters that becomes very complex and so on and so on. But you need to improve the physics and the physical knowledge, and only in this way you can improve the methodology based on artificial intelligence. I don't think that it will be feasible, really, to create, for example, a unified physical model of solar activity. But we can understand more and more, and then use the artificial intelligence to, say, fill up the gaps that we have in our physical knowledge. There must be a sort of combined, as you stressed, hybrid approach. But only the physics is not sufficient, and only the neural networks or artificial intelligence are not sufficient by themselves.
Okay, thank you for the question and for all this discussion. I think that we can continue in the next after the break, and we can continue discussion exactly for all these stuffs. What the idea of this panel is more to presenting and to provoke discussion. Then we can continue after the break with more deeply discussion, and I actually encourage you to do it. I see that we have two more questions, and also Gutiérrez would like to continue discussion after the break. But I see that just to be prepared, Professor, after the break, if science models are not that interesting in an operational framework, what about the potential of AI algorithms for the forecasting aspect? And another question is there a plan to incorporate these NC and FC functions you spoke about into NATO's operational networks in corps and brigade level? Yeah, it's interesting questions. But before to continue and to go on the next panel for discussion, I would like to finish first of all with presentations. And our last presentation is by Noah. Thank you again, Professor Masarotti. I'm sure that we will continue with discussion panel, and you have a lot of things to share with us and to ask you, or you to ask someone. Angela, you still have a question, or just you raise the hand? You forgot to raise down. Okay. Please, our last presentation, and after that we will make a short break and we'll continue, as I mentioned, with discussion, is Dr. Tzu Wei Fang. I hope that my pronunciation is quite good. Dr. Tzu Wei is a research scientist from the University of Colorado. Her expertise is on numerical simulations of the ionosphere and thermosphere system. She has been leading the development and the operational effort for the WAM-IPE model and SWPC. In this talk, she will provide more details of the model and demonstrate the new products for thermosphere and ionosphere forecast. I would like to excuse myself because I'm quite new in the abbreviation in that area. That's why sometimes I cannot switch very fast. Thank you, Dr. Tzu Wei. The floor and screen is yours, and please to present your presentation.
Okay, thank you very much for having me here today. It's my pleasure to join this group the first time. So I am going to talk about this model framework, but first of all, I totally agree with a lot of perspectives. What are the concern and needs from these operators and users are really critical for us physicists to understand the problems and prioritize the task for development of space weather modelings and monitoring system in the future. And this is an example of the model development and come out of past 10, 15 years of our center. So my name is Tzu Wei, and then there are several people in my operational team that I would like to acknowledge. Sorry. So there are several operational models, which means the NOAA has maintained this model running 24/7 in the NOAA Supercomputer Center. So there is one the RG NLEL model and the Space Weather Modeling Framework Geospace model. Those has been transitioned to NOAA operations and now providing real-time space weather product. So some of you might know that WSA NLEL follows the propagation of plasma from Sun to Earth through interplanetary space for arrival time of coronal mass ejection. And Space Weather Modeling Framework Geospace model simulate the response of near-Earth magnetic fields for impacts of induced current on power grid and impact of the energetic particle on satellite systems. So transition this WAM-IPE model to operation adds an important link in the Sun to Earth modeling framework and enhance our capability for forecast space weather in the US. So what do we care in terms of thermosphere, ionosphere, and what our model can produce is listed here. So for HF communication, the change in the minimum usable frequency, LUF, due to D-region absorption has been captured by our model called DRAP. And changes in maximum usable frequency, MUF, due to the peak plasma density and peak height of the density And undulation of bottom side F region can be captured by this new model that we just put into operation. For satellite positioning, navigation, timing, and communication, we care about the mesoscale structures and gradients in plasma density, which cause the radial diffraction and cause amplitude of phase fluctuation in GNS signals. And you also delay a navigation signal due to line of sight electron content caused by the position error. And also, we cannot produce this in the model at this point, but small scale ionosphere irregularity, we can cause simulations and fluctuation or complete loss of signals. And for satellite drag, this model can produce neutral density product, and which is very important to account for the uncertainties for decision-making, maneuver planning. So the ionosphere thermosphere, the upper atmosphere actually has significant variability, just like the troposphere weather system. The system is driven by the conditions in the incoming solar wind, solar UV, and solar EUV radiation, as well as the wave tides from the lower atmosphere. So whatever you see tides and wave in the weather system, you can see does have an impact all the way up to 500-600 kilometers that we care and where your satellite's flying. So the lower atmosphere forcing, including the longitudinal variations in the tropical convection, which drives non-migrating tides. And southern stratosphere warming event can modulate the migrating tides that impact the electrodynamics in the ionosphere. There are also important tides called terdinal tides that create the nighttime features in the thermosphere and further impact the ionosphere and the plasma. And also we have very significant background variability that we were trying to capture in our model. So the model called WAM-IPE. So the WAM is whole atmosphere model, which is extension of US weather model based on the global forecast system spectral hydrodynamic chord up to 600 kilometers. And it does have 150 layers with gravity, very high variable gravity. And it provides different species, O, O2, O3, N2, and H2O for all this dynamics. And the WAM run in about 180 kilometer resolution at this point, which is called T62, which is much coarse compared to the operational weather model, which is 12 kilometer resolution with T1534, which is probably weather community would know that better. So the model includes all the lower atmosphere weather and dynamic processes, as well as the additional thermosphere ionosphere process and physics. And they provide a 3D field for neutral winds, temperature, density, major species, and compositions of all the neutral particles. And WAM coupled with IPE, which is our ionosphere part, was based on the time-dependent three-dimensional regrading in space weather mediator that developed within NOAA. And right side movie just show how dynamic the model looked like before the storm and during the storm. So this is 2013 about G2, geomagnetic storm, the neutral density perturbation. So you can see that when storm hit, there's strong perturbation coming firstly on the high latitude and propagate all the way globally. So our model can capture this. Sorry, I think it's 240 kilometer. I'll show some other result later. And this is just the IPE, which is neutral atmosphere part. We also have ionosphere plasma's electrodynamic model called IPE. It's a plasma component of the atmosphere. It's time-dependent global three-dimensional model of the ionosphere and plasmasphere from 90 kilometer to more than 10,000 kilometer. It based on the flip model for the flux tube solver to solve each flux tubes. And it does include the seamless perpendicular transport from pole to pole. And we do have proper empirical drivers in high latitude to drive the model. And the model provides the plasma density, velocity, and ion electron temperatures and in the ionosphere and plasmasphere. So right-hand side top just show the grid of the plasmasphere. And then the bottom side would kind of just show how dynamic for 9 different species and changing in different grid and with the time. So we're able to capture all these dynamical changes in each grid. So WAM-IPE has been developed with a workflow that goes into operation. So in terms of operation means the model is going to run by itself for 24/7 with proper drivers. So we have 2 particular ConOps that are designed for the model. One is including the troposphere weather all the way to upper atmosphere model. So with the forecast we do provide 2-day forecasting events based on the F10 and KP. So this ConOps particularly include the low frequency atmosphere data. So we do have the lower atmosphere data simulation up to 60 kilometers based on the National Weather Service global workflow in every 6-hour cycle with the data simulation system. And then whenever we have the solar wind values, the model take the solar wind value beyond the real time in the forecast, we start to take the forecast value coming from our space weather forecast office. The cutoff suites capture the near real-time space weather solar wind conditions. So in this particular cutoff, we run the model in real time, taking the best troposphere definition, and then ingest solar wind data, follow the real-time observation in every 5 minutes. So to actually capture the onset of storms compared to the CONOPS one. So we think this two CONOPS one, we hope these two CONOPS, we are hoping that we can capture most of space weather event. So I'm just going to show a few movies before the end of talk. So this kind of showing you that how well the model is capturing one of the storm, which is 2015 St. Patrick's Day storm. And in this particular storm, the storm started to hit on the 17th of AUT. So you will see a lot of perturbations before the storm, and you can see how things changed in the storm. And this movies, you can see top side is the neutral density of 400 kilometer. And the bottom right shows the neutral density anomalies compared to the quiet time in percentage sense. And left bottom side is O&2 ratio, which is a good indication of how ionosphere circulation, thermospheric circulation will be impacting ionosphere. So I'm going to play the movie. So you can see that before the storm hits, neutral density variability is very small, but you can see that a lot of structure start to hit when the storm comes. And this particular storm, we have about 300% neutral density increase, which can be a quite big hazard for space traffic management and your satellite trajectory prediction. And you can see that when the model goes to second day, the O&2 ratio shows a very big decreasing in near Australia, Southeast Asia area. And that's where the negative storm impact coming into the model. So that will be the time that we start to see ionosphere has a decreasing due to the storm. So I will show you that some of this ionosphere change in the next slide. So then you can see that once the model get past the neutral density anomaly reduced significantly, then get to a normal condition. And then now I'm going to show you the same storm, which hits about AUT. And on top are the TEC, the total electron content, and maximum usable frequency. And the bottom are the TEC anomalies and MOF anomalies in percentage sense. So the storm, I was going to play the movie. So you can see that the storm, before the storm, actually, there are a lot of day-to-day changes and a lot of anomalies already there in the TEC and MOF. But once the storm hits, their changes are dramatic. So you can see that there's more than 120% of TEC anomaly happened. And then in MOF, you can see there is strong reduction. There also is strong enhancement during the storm. And then once you go to the second day, you can see that in Australia sector, which I was saying that there's a strong negative phase impact, a negative storm impact. You can see that TEC reduced a lot and MOF is significant reduction. And some of this reduction in MOF goes about 25 megahertz during this event. So got to be really careful when you select your high frequency band for your communication. And this is the global view. What I'm going to show the last video is probably some people are very interested in this European view. So during the same storm, you can see that, and then bottom side, actually, we're showing the absolute TEC and frequency changes during the storm. So you can see that there are a lot of fine structure in the TEC and create a very significant TEC gradients during the event. And then in MOF as well, you can see a lot of bands, a lot of dynamics going on in the model that can capture a lot more finer scale things that we cannot be seeing before. So I think this model provides us tremendous capability in the future to predict the system, in few days in advance and taking the best condition that we can have. Yeah, so you can also see that this negative storm has a strong impact in this in the whole area in the North Hemisphere during the second day. So that's all what I have. The model has been transitioning into operation, and actually we are working on the final stretch the model. So hopefully by end of this month, we will be fully in operation and we'll start to provide product in the near future. And our product, including the TEC and MOF and then thermosphere neutral density, that will be used as Space Weather Forecast Office for issuing warnings and alerts. And then we have a lot of development actually on top of this. We are trying to engage the user community, like you guys are welcome to give some input on how we should improve our product designs. And then we are working very hard to produce high resolution model to actually be able to capture some of the smaller structure ionosphere disturbances or irregularities that does impact a lot of operational system. And we are also extending, we already have done that, the neutral density output to extend the model output from 600 kilometer all the way to 1,000 kilometer, since there are a lot of objects above 600 kilometers. So if you're interested in looking into how the model can produce, can be used in your orbit propagation, that will be welcome to take our data. And then we also going to develop this new whole atmosphere model based on the final volume cube sphere dynamical core, a V3 model, which is the latest US weather forecast system. So we are hoping that developed based on this new dynamical core could produce more space weather changes and then can capture a lot more of the troposphere impact in the upper atmosphere. That's all what I have. Thank you very much.
Thank you very much, Dr. Frank. Actually, it's not that's all what we have. Actually, that's what we need. Thank you very much for this presentation. It was very valuable for us, and I'm sure that Dan and other our lecturer and presenters here also has a lot of questions inside. But first one, two questions. If someone would like to ask. If it's possible to stop sharing, please, just to see if there is someone with raised hand. I don't see someone. Oh, yes, we have a. Yes, please.
Hi, Dr. Safwan. Enjoyed your talk. Couple questions. You mentioned something about in your model neutral densities at 400 kilometers. And that affecting satellite trajectories, etc. If I remember correctly, this ISS flies around that altitude. Have you used your model to see what the how much can you predict and how can you validate any of the model predictions?
We have not looked at it because our focus is still developing this model and getting this data out. And we're hoping there are more people start to use our data can help with that. But we do start to work with some of the group to look into, for example, some of this, a lot of Starlink satellite. How does this prediction will help with better propagate all this moving parts in the space, and how does that impact the nearby object? But we are not there yet, but that's a direction.
And the oxygen to molecular nitrogen ratio, that's a temperature indicator, isn't it?
Yeah,
because of the scale heights being so different.
Yeah, that's basically change with the thermosphere heating, and how does that change the contribution between the N2 and O2 in the bottom goes up.
So I mean, you have an incredible opportunity to, now that there are thousands of satellites, and you can, use their position and then their, effects of storms. And as you pointed out earlier, that there hasn't been any major storms, so you can't validate them. But is there any limit? Since you're doing a model, you have, blank slate, so to speak. So you could put any larger or smaller perturbation to see what happens to the orbits. It'll be rather interesting to try those out, or maybe even create an experiment that'll actually do that.
Yeah, that's our next target. Yeah, thanks.
Thank you.
Thank you, Professor Chakrabarty and Dr. Feng. My intention is now to make a short coffee break. Actually, here in Eastern Europe is almost night, around 8 o'clock, but okay, for me, the coffee is always valuable. To make a 10 minutes coffee break and to continue with the last panel about discussion of all these questions, and all of you to share your thoughts and to make valuable conclusions. Okay, thank you, and see you after 10 minutes. Let's see, at 7:40 is here, but I don't know what time is your time zone. After 10 minutes. Okay. See you. Okay, I hope that you had a short break. Now you can switch on your cameras. Yes, thank you, Professor. Done. Can I see you? See who is here and to watch ourselves. By the way, if it's possible, technical, to make a one picture screenshot, just to have it for the day. Yes.
Hey, no primping in the hair.
Would you make in a picture plan? Yes. And please switch on your cameras. Can expel Konstantin Lazarov, he is here.
Sorry, I don't have any camera on the computer.
Ernst, are you here?
Yes, but I'm sorry, it seems my camera didn't work.
Okay. Dr. Fang? Professor Vasilev?
Sorry.
Sean Young?
Yeah,
Audio? I'm still expecting someone to switch on your cameras. Dr. Fang, please switch on your camera. Yes, thank you. Jens?
Here.
He was here, yes, I'm sure. Okay, make a screenshot, please. Okay, thank you. And now, Dan, actually, what we're expecting in this discussion to continue is to clarify what kind of models, operational impact, contingency plan, and of course, artificial intellect to continue the discussion. Dan, could you say some words?
Sure. So first of all, I'd like to say thank you to all of our presenters today. I think we had some excellent talks, some excellent questions, and some excellent discussions. And I hope that continues for the remaining part of our discussions this afternoon or this morning or this evening, no matter where, depending on where you are. I think the thing that we want to get to at this point, as I tried to get to in the introductory talk, was really we have a lot of models and we've seen a lot of the discussions, but there are still questions in terms of what comes next. What are the things that we should be focused on collectively as a group? Are there models that need to be continued to be improved? Are there data sources we're missing? No, I certainly have my own opinions, but I would like to collectively discuss it because we all have different backgrounds. We have strong scientists and some engineers in the room. We also have some operational people, and we also have some people that don't have a lot of space weather experience. But that's kind of what I'd like to get to. I'm willing to open up the floor. It's what are we missing from a science point of view or an engineering point of view? Are there models that need to be fixed? Are there data sources that need to be brought in? Is it, I guess I'll leave it open-ended. I'll just stop talking now and hand the floor over. Does anybody have any thoughts or questions?
Okay. Let's start, Konstantin, maybe with you.
Thank you, sir, for the opportunity. Yeah, the modeling of space weather and trying to make a precise model capable to forecast the parameters is something interesting from a scientific point of view. But in my personal opinion, for me, it will be much more interesting working here in Crisis and Disaster Management Center of Excellence to see what is the relations between the space weather and other processes. And I saw actually during the presentations that such researches are already done. And I think that our proposal is in the right direction. Dr. Fang, for example, said that we need really good data set in order to make or to develop a precise model. I absolutely agree with this statement, because if you'd like to cover significant or the necessary range, actually we should have such data. I mean, covering the extreme values. However, I still believe and think that such comprehensive research in that direction, seeking for correlations, will be useful for us, and not only the people involved in this process, but also for the society. Thank you.
Yeah, it's correct, and actually we saw some models and some already implemented programs, as Professor Massarotti, I think, and one of the questions was, you are talking on strategical level, but one of the questions was these functions of NC and FC you spoke about in incorporating NATO's operations networks could be incorporated on corps level and brigade level. It's almost tactical and operational level. This is another question which we would like to understand. And there also was about potential of artificial intellect algorithm for the forecasting aspect, which you already spoke about. But let's hear your opinion, maybe Professor Massarotti.
Well, before that, I will just say a few words regarding the models, because I don't know exactly what is or what are your goals in this sense. That I guess that the most important thing is to avoid reinventing the wheel, in the sense that there are many efforts all over the world of creating centers where models for space weather are integrated and they are just developed having a good interfacing related to the different operational domains. For example, I am thinking to the Community Coordinated Modeling Center at the University of Michigan, or the ISVAT effort that is promoted by COSPAR, or the Virtual Modeling Center that we have in Europe under the European Space Agency sponsorship at the University of Leuven. So I wonder if you want to develop models by yourself and limit just these models to the military environment, or you think you can use also models developed at the civilian level that can be, for example, customized and upon upon agreements then used in the military environment, because there is the risk really to reinvent the wheel, because there are very many efforts that were also sponsored by the European Commission and so on, and the United States as well. So this is the first question that I ask, because I don't have an answer really.
So I can provide an answer for that, Professor.
Yep.
So the intent is not to
question
reinvent
done,
the wheel.
please. Yes.
The intent is to see what's out there and see what potential gaps are out there in terms of what data sources are we missing. In other words, do we have everything that we need to make an accurate or as accurate of a prediction as we can, right, in terms of a forecasting capability? Right? I'm a little less concerned with nowcasting, because nowcasting limits my capability to react to any kind of space weather event. Right? Ultimately, I, as a military member, looking at it from a NATO perspective, I want to preserve the space capability that I have, whether it's your PNT, whether it's your ISR capability, whether it's your communication, right? So I want to leverage the tools that are out there from the collective labs, from the collective organizations, right? And I think the intent of why we drafted this activity was to think, okay, let's assess what's out there. Are there things that we should improve? But more importantly, take that information, integrate it from the multiple models, and then act upon it. In other words, how do I preserve that capability? Do I need to save my satellite system? Do I need to build additional redundancy? Those are the types of things I think that we're trying to get to. So the intent is to do a survey of some sort of all the models, but really it's to move beyond that, right? The models are what they are. We can make recommendations to the nations, to the labs, to say, hey NOAA, hey NASA, hey DLR, hey DSTL, anybody, go improve your model. We need this information. But the reality of what we need to focus on, or what I think we need to focus on, is, again, back to what I said at the very beginning a couple hours ago, it's the so what. How does it impact operational capability? What information do we need? So in my mind, the question we should be asking is, do we have the right output? And if so, how do we act upon it? I hope that helped.
Yeah, but I wonder if you considered all the tools that are available at the United States Air Force, because the wing that is managing with space weather, they have a lot of tools. Many of them are not open to the public, of course, and so this, of course, is something that should be also considered, analyzed, and so on, because perhaps many of the answers that you want are just intrinsic to having this kind of survey.
Maybe I'll say something about this. So what I see with this whole question is, I still feel things are really detached. So my background is physics, like we are as research scientists, that we really build a model with all the physics we know. So we pull out this, and now the next step is, what is the impact on your system, which I don't really have knowledge with. So how do we engage these two groups? So for the user perspective, how can I say, we have been talking about subsidies, how do we get the feedback? How do we get the real-time impact back to our center to evaluate how well the model is doing? That is something has not been established. And with your big membership with all the utilities you guys access might be a very useful thing, is to provide us impact. If you see there is some impact, might be related space weather impact, then we can at least get that information. So we usually release the information of environment, but we don't get feedback on how does this being used in your environment. So that's one thing I see. And the other thing is, we will keep on improving the model through various methods. The one important thing is how do we get more data into the system, not just for AI model, but it's extremely important for physical-based model to be validated against with something. So for example, neutral density, I don't have an in-situ neutral density measurement flying constantly right now that is reliable to do real-time comparison. So how do we know if model is doing a good job or not? Yeah, we can use some inferred data, but they're definitely not as good as what we would like. So once we have this data, how do we ingest into the system to really improve the initial condition for the data simulation so that we can move forward for the forecast? So without having a good nowcast with the proper data simulation, it's a little bit hard to tell you what happened 2 days from now. So I think what I see this problem is, how do we engage all the resource people have to improve and get more data so that we can work more collaboratively? So maybe what you guys have is data, not model. Or what we can support will be the model system and how we can share that information. So getting the data and really getting the user's feedback and getting the impact. How does it impact your GNS signals and the real-time system? How does it impact your communication signal? But some of those are classified. So we never get those impact on how well our model is doing or even being used in some of these operational systems. So that's what my feeling on where we are at this point.
Yes. Actually, that's a very, very valuable thoughts. And I think that everything is clear. We know that have a lot of models. We know that they have a lot of results where is going to support some organization or some governmental and etc. Here in our group, and maybe I think that Dan will agree with me, is more to find how to collaborate, how to use these results and to provide that information, those results, and how to help to our forces, to our allies, and to collaborate together and to have a common results. That is more important for us as a point of view of NATO and as that kind of group, and to deliver what kind of impact could have all this what is existing on the market, how to deliver this very smoothly and on time for our allies and for our forces. That is most valuable from NATO point of view, I think so. Dan?
No, I agree with you, and I'm thinking through the problem set. I mean, unfortunately, this is not the first time this question has been asked, nor will it be the last one. Right, bridging the gap between what the operator needs and what the operator sees and what data is releasable with a scientist and engineer. Right, how do you validate a model? How do you provide that information so that there's feedback, so that that model can be improved? Right. But then I would argue, so again, my background is a space physicist, but I'm also a military officer. So I can see into both worlds. I don't know if I have a true way to answer the question. I think providing forums such as these is a first start. But in terms of a regular frequency where it's a regular process where it's not dependent on personalities, that's where I struggle. I think this activity is a good first step to identify, look, these are where there are deficiencies between the two communities, right? And then looking to build those mechanisms so that there's a reporting function of some sort, right? So I'll tell you, I'll give you an example. I'm getting ready to fly 3 LEO small sats, and I'm doing it under wearing a NATO hat, but I'm also wearing a US Air Force hat, right? And soon to be a Space Force hat. I'm pretty familiar with a lot of the stuff that's taking place within the Air Force Research Labs, which was just recommended. But I don't, even though I'm a space weather guy, you know, I don't live that day to day. So, you know, so where's that mechanism I can go to the space weather community and say, hey guys, I'm going to fly a couple satellites in low Earth orbit in LEO. Do you have any sensors I can throw on, because I'm going to be in the upper ionosphere for, you know, the next year, you know, so there's not that feedback loop that is apparent to me. So I don't have an answer, but I just wanted to make sure, you know, we had that discussion. I think this is part of the value of our discussion, right? Identifying where there are deficiencies in either a process, or identifying where there are deficiencies in the models, or where there's output, right? Or maybe input.
Yes, please.
I'd like just to add some comments. Completely agree with Colonel Dalton. And talking about the practical side of how we could validate and could test how accurate actually is the model, the practical solution is that we separate the initial data used for the training of the algorithm. The golden ratio at the moment is 80% used for the training of the model and 20% used for the validation. Of course, we have to pay attention of these two groups in order to have good results at the end. But it's how to say, it's excellent solution in order to validate the model. And as I said, absolutely agree with Colonel Dalton about our aim and goal to fill what we already identified as a gap into the knowledge and especially into these practical instruments talking about space weather, because modeling just space weather as event and process is, as I said, is not so useful for the society, but linking it with other processes is something very useful. And sometimes we could expect really interesting results if there is such correlation between space weather parameters and behavior of specific birds, let's say. And these birds are located near to air base, for example. Of course, it will be interesting for us and could be useful. What is the impact because of the security and safe of the flights? Over.
Yeah. Angela, I think that you would like to mention some thoughts. Unmute, please. Unmute.
Okay, is that better? I said, can you tell from my expressions? No, it's you look, it's a complex problem, and you know, I'm hearing let NASA, let whoever tell us what the models are. Okay, if we're trying to compare, you know, say we're going to work on sort of the models that are given to us, or the models that are considered the current state of the art. But I go back to the question that Mauro and I started sort of on his discussion. This is we are talking about the complexity of the real world of the forces that are on, and it's all, and there are physics and there whatever. But it depends where we want to have the cutoff in this grouping. If we want to say we're not going to start and look at the, you know, the non-linearity, the complexity, all the things of the complex environment, we're just going to take what the status quo is, and we're going to try and get data and do that, and that's a hard enough job. Okay, but if we, you know, if we are concerned about the dynamic changing situations, applying machine learning, you know, machine learning techniques, these are very robust techniques, as I said. But, you know, we as a company, and, you know, you've maybe been asking as we've participated in these workshops, what use might we come? We do work in a whole variety. For example, we worked on a problem which is about the survivability of a heat shield of a spacecraft going through the atmosphere of a planet, let's say the moon of Jupiter. And, you know, and the engineers in ESA who were trying to design or predict the design of that heat shield for 15 years, the engineers and physicists had been looking at, okay, it's a multi-physics problem, and we've been trying to engineer using all of the, you know, what we would say is with the heat and the speed, we're in the plasma state. Forgive me if I take a little minute to describe this, but it's quite, I think it's pertinent. So we're in the plasma state. So there's the Schrödinger equation, the Born-Oppenheimer, and they've been trying to work with this established sort of it's physics, okay, quantum physics, to deal with this quantum-esque situation without success. When we combined an understanding and a vision of the physics, we revisited, if you like, a new mathematical expression of that, rather than trying to take some established model of physics and then sort of data. We were able to come with something which was tenfold much more beneficial to the engineers. And believe me, some people were elated, some people were depressed, they'd spent 15 years, but they hadn't looked at this. And I just don't want us to, you know, we have to decide what our objective is in this grouping. And if it's to give us a standard model, we'll just answer that, we'll answer the exam question. Or if we are saying we do want to look at the complexity of the environment and have some kind of adaptive approach, and you know, and AI is capable of dealing with that adaptive approach as well. Over. Yes, that's what I wanted to add, but I'm not sure in this medium we can. This is something we should be having a glass of wine tonight over and having a great discussion on, I think.
Have a beer instead. But Angela, I like your thought process. You know, so it really, I think at the end of the day, or in this case, the end of the afternoon for many of us, or the end of the evening, we really need to figure out how we define success, right? So for me, I define success as identifying deficiencies, making recommendations, and trying to come up with solutions if we can, but really identifying the problem and trying to make recommendations. For me, I think that's success in these types of activities, as I've learned. I mean, I don't have a huge amount of experience with the S&T activities here in NATO, but given the fact that I have no budget to spend here, I mean, I have to be realistic. So for us, trying to determine what models are good, where there are deficiencies, what are the products that we need, where are the sensors, where's the analysis good or bad, and making those types of recommendations. And I think ultimately, again, where I would love to see this go is if we have the operators to start to determine those courses of action, right? Say there is a space weather event that is taking place and all of a sudden my radio communications, my comm is poor. What do I do? What are my courses of action? How do I maintain that service, that capability? Or extrapolate it to something else. All of a sudden we have a space weather effect. It's, I don't know, a substorm of some sort. And now my PNT is being affected. How do I adjust my satellite system? Do I just live with the consequences, right? It's the so what piece that I keep getting to. It's what's the impact from the science piece, which is cool. And part of me says, that's great, let's focus on that. But the realism or the realist in me says we need to focus on the outcome, right? So in my mind, we need to balance the two. What's the science that we need to focus on? And then what's the impact? What do we do with the systems and how do we mitigate it? How do we mitigate risk? And what do we do to maintain capability? Sorry, I'm off my soapbox. That would have been much better with a glass of wine in your hand.
If I could come back in, and forgive me if someone else wants to speak, because there's lots of hands popping up. But I think there's an artificial, and honestly, if we could meet, we would have a great. I think we would have a great brainstorming. You know, I think there's an artificial segmentation of let's do the science and let's do the data and let's, you know, I think the example that I gave is where you break down those. You're actually coming at a problem and looking at it, thinking first of all of the complexity of the problem, and then deciding what science and what data science and what algorithms that, you know, and what data have you available. I mean, it's that piece, and I think we would have a richer, because we don't do this for the sake. We're not an academic. I don't mean to say this, but we don't produce academic papers. We produce results for industry that engineers can act upon, that our Space Force can act upon, that are operational people trying to drill very long holes in the ground or understand how to sequestrate gases that we don't want to leach back up, having made a big job of putting it there. It's very operational, it's very pragmatic, it's very industrial. So I want to say this softly. I don't want to see as if I'm a cat amongst the pigeons, but I want us I would encourage us to see, let's not try and cut off and say that it's the science, it's the data science and its output. This is all about an end-to-end, having a very pragmatic, operational, but highly honed solution. And we have an opportunity. We're in the 21st century. We can do this. Data is a gift, but it's only a gift if we maybe look at how we approach a problem a bit differently. Over.
Yep, thank you. By the way, you said glass of wine, and we already took it, and we can continue. Professor Maserati.
Wow, that was just wrong.
Professor Maserati, you raise your hand, please.
Yes, as Colonel Galton was considering the aspect of integrity of satellites in the NATO framework, I advise you to find out a document that was the outcome of a specialist meeting that we organized under the framework of CSO, that is called A Day Without Space. But I don't remember if it was classified or unclassified, because many of the parts of the outcome are classified because we consider the different kind of weapons and so on and so on. But it can be very interesting to you to just go through this document. You will find in Science Connect, I guess.
Yeah, any thoughts from your side?
I don't know. I think everything has been said, so nothing from my side.
Okay, just to be sure that because
yeah,
you were here. Okay, actually we have some thoughts, and I think that we have a good conclusions. Anyway, we will continue to work on all these issues which we mentioned about. I'm sure that we will continue to collect different models as a work of the group. We'll continue to see what kind of data and way existing. That is another it will be something like a final result from our group. I really hope that Konstantin will continue and Gutier to continue to work on artificial intellect and how could help, especially from Center of Excellence, Crisis Management, Disaster Response. It will be useful for us, and me as a director will be beneficial for me also.
A quick comment on that, sorry. I was just thinking that there are a lot of methods these days also include the physics-based model simulation into the AI technique. So it might be something to consider, just have some of this physics into the system instead of just data.
Yeah.
Sorry, I didn't mention. Sorry.
I agree. Yeah.
It's a completely open. Please continue. I'm just.
I just thought this is something that newer technique people are trying to incorporate so that we might be able to steal our thoughts out. That's interesting. So I think that's something might be open to bridge things between so that we can provide more capability.
Yes.
Actually, Dr. Frank, it's very interesting because in our Center of Excellence, we created a specific repository. Actually, it includes engine capable to run different models related with disasters. Because we found that military simulations, especially, there is significant lack of such precise and good models. And the impact of military operations is significant. That's why we created such a repository and engine outside of the military simulations. And now we are able to transfer the computed object, because it's not only a picture, but it has specific parameters. We can transfer it to any kind of military simulation, like JCATS, if you are familiar with this military simulation, like Massa Sword when we're talking about the French one, or Cora, the German. And it's done simultaneously with same parameters, and it's very useful actually to have it and to see what is the wargaming when there is a disaster. Maybe we can use the same approach with space weather models, and we can add them in our repository, such model, in order to see what is the effect during the wargaming of a military operation.
Okay, but my question is again, who will use it? Who will make these models and the results from the models? To whom to provide? That is, I think that the question of Dan, that we should include here operators, and we should be somehow not to stop the chain and to deliver to the commanders and end users.
Actually, that's the answer. The headquarter and the commander will be the users of
who from the headquarter, and which HQ will want this information and for what to use it. Yeah, these are questions which we should consider in our future work, of course. And I'm sure that there are a lot of even in some armies there are some units which are talking about that kind of usage of that data. Yes, Angela, please.
So a topic which I think we are all pointing towards is it's a phrase which we're looking at, which is what the commanders want is they want decision quality, intelligence, knowledge, information at the speed of relevance, and so it'll be whatever we're dealing with a complex environment. We're trying to monitor it, we're trying to capture it, we're trying to put clever algorithms to capture it and give outputs which are in fact, as we say, you know, it's not just it's not just a simple sort of we cranked a handle and we spat out something which was a standard view of the world. We're actually trying to give them the situation they're dealing with now, perhaps multi-source, this heterogeneous data that's coming in, and giving them these these decision quality information, and at the speed of relevance for them to turn that information into actions, into wisdom, into understanding, and something they can act on. And this is the premise that we, you know, we can bring to this community, if you like. I don't know how we do this in workshops or subgroups, but it's what we're working with. We really would like to work with NATO. We, you know, as you've heard, we've got a French, British, I'm half Italian. You know, I don't want to just say it's all about what we're doing for the UK. We've also got a Norwegian company we've just established. We think NATO. We don't think, you know, the country. You understand me. I don't want to get politically incorrect here, but
yeah.
So that's what I would say the domain is. It's about this decision quality information at a time. Sorry if I'm overspeaking.
No. All thoughts are well accepted, and actually I would like to just to remind that here is a Chatham House, and everyone can tell what is his opinion. Absolutely free. Dan, you raised the hand?
I did. So I think I can answer one question, or at least it's one foreseeable future. We ask where this data should go to, and I think the intent is the Space Center at Ramstein Air Force Base, right? At least in the next 4 to 5 years, it's envisioned to be a data repository, right? And so when I ask the lead officer who's helping define the strategic vision, you know, his hope, I think, is to grow it more than that, right? There will potentially be operators sitting on console controlling satellite systems if NATO goes down that path, you know, 5, 10, 15 years down the road. So I think that is one possible future, and I think that is an easier way to kind of vision where this lands or where this goes to. In regards to thinking about who the information is for, I would almost argue that it's not the commander as much as it is that person sitting on console. And I would like to get beyond the person sitting on console. I'd like to get to a point where we have data inputs coming down and you have autonomous reaction, right? Things, machine learning, machine-human interface, that there's a trust quality that allows something to take place at a much faster rate, speed of relevancy, to steal some words, right, Angela? Right? So that you don't have to worry about that. Right now, if you are informed, then you have some codes. I think that's where we're trying to go to, or at least it's in my mind vision.
And I stole those words. I stole those words from Harv Smith, our strategist of the Space Command. He's I don't know if you know Harv, if you've ever met him, but Harv Smith.
I have not, but I just put that in a legal framework paper for space. It just seems to be the buzzword, right? Speed of relevance right now. So that resonates with me, because you need data when you need data, right? And how fast you get data sometimes determines how much time you have in your course of action, right? So,
yeah, and it's
I digress a little bit, but I want to bring that up.
And you mentioned another really important word, which is trusted data. So it's decision quality, and it's how do you get something that is a trusted reasoning system. I don't want to plug, but it's a look. We started our business in 2008, and we were working on the Franco-British systems of creating trusted reasoning architectures. That's what it was called back then. We, you know, for various reasons, we moved into the oil and gas and we started doing it. But all of these concepts are very relevant. And yes, I think what you're saying as well is commands now want to have trusted, they want to have it distributed information and know that everybody who's in those distributed locations are all looking at the same quality and coherent information, and therefore using their intellect, their wisdom, to act as best as they have been trained. And I think that's how we're going to get the best possible you know, outcomes for what we're trying to do. And all of this, yes, AI, machine learning, and those great algorithms and whatever structures we put will be important. But yeah, I think the mission is that distributed decision making, but based on trusted decision intelligence at the speed of relevance. Sorry if I'm just repeating you, but yeah, it's exactly where all of this is at. Over.
Yep. Thank you.
So I would guess, I'm
Yes,
looking
please.
at the clock and I know we're about 20 minutes over from what we had initially started. Let me ask a question, because I feel like we're starting to circle a little bit around a few things. What are the next steps? I gave you my recipe, at least my thoughts for the next steps forward, right? In my mind, it is continuing to look at the models, but now starting to identify where there are gaps, right? Where are their weaknesses? What are the things that we lack? Right? Are there data points that we lack? Is it data itself? Is it sensors? In my mind, that's kind of the next step. What do we need to do to kind of move forward, right? We've identified a few things. There's some goodness in some of the models we've looked at. But I guess I just want to open up to the rest of the group. What comes next? I mean, you saw my output or my thoughts on my slides, but I'd like to open it up to anybody here. What do we do next? Because I don't think it's about choosing a specific model or technique. That's not the point, right? All the models have some value, some intrinsic value, have some capability. How do we integrate those outputs, right? Do we need to integrate those outputs? Maybe, but maybe not in this forum. But certainly, in my mind, as I mentioned, it's identifying what comes next. Those are the recommendations we hand back to our respective science and technology organizations, right? And we say, look, we've identified this as something good, but more importantly, we've identified this is a deficiency. This is what NATO thinks is a collective, right? Because we have a group voice which carries much more weight than an individual national voice.
It's correct, and I like this one, but are you sure that we can identify all gaps, or we should identify some gaps where we can work and to deliver some product? Maybe it's better.
We'll never be able to identify all
the gap
gaps.
where we can deliver something.
No, I agree with you, Orland. We'll never be able to identify all gaps. I look at our list of participants that I'm aware of, probably 7 or 8 space physicists, right? And nothing against the colleagues here. They all have an area of expertise, and there are some that are probably very broad and very, very smart within the area, but you know what you know. And I don't think that the intent is to identify everything. It's not I did not envision a broad survey of every single model and looking where there are gaps. It was simply to try and identify a few of the gaps that are relevant for operational impact. In other words, what do I prioritize as a commander? In my mind, what I count on NATO is COM, ISR, and to some point, some aspect PNT, right? Because you have GPS and you also have European capability. But in my mind, those are kind of the 3 areas that we focused on. So where do we need to focus to understand the operational impact from space weather events on those 3 capabilities? Or I'm open to other mission areas, but to me, that's how I define a problem space. You have to bound it a little bit. Otherwise, we'll still be having the same conversation a year from now.
I think there are a lot of activities within NOAA or in the US side is to understand or build this space weather architect. So there are a lot of large scale activity going on. So you might not want to repeat that activity just to figure out what is useful information in our system. But I think the other thing that Space Weather Prediction Center has been trying to put our foot on is trying to establish a test bed, which is really something that we want to bring in a place that we have people like, operators and users and talk directly to the science engineers and scientists engineers. So how do you guys, maybe how do you bring in that piece of information into this whole big loop would be probably very useful instead of trying to go back and see what model is useful, what data is useful, because a lot of big group of community has been working on it.
Sure. So I guess I would turn around and ask you, to what extent, or to what is your end goal, right? So you have a predictive.
So,
what do you do with the data? Is it public source? Is it open source? Can anybody access it off a website? I mean, where I'm looking at is how do you distribute it to the operational community, which I think you're trying to crack the nut on a little bit.
Yeah, I guess so. But our information is going out publicly. If you sign up our services, everybody can get it. Even I'm from Taiwan, and I know they mirror our results back there, or some of those centers has been mirror our results. So it's not secret. There's no secret in what we put out. Whatever we serve the world. So how do we actually improve the services, and how you guys get the information that I'm really new to this, but for our perspective is how we can get all your information so that can help us make some of this decision is critical, because we are kind of living in a box that without knowing what happened in the world. So my question is, how can we get, because without getting feedback, then I cannot guarantee what information we give is useful, right? That's what our concern is. We have a lot of information, we can give it out, maybe find a way to give it out equally in good quality, but how do we guarantee that's a good quality? That is my concern. And you have such a big group, there must be a way to get something that within US that scientists cannot obtain.
This is very interesting question, because we can finally deliver some information which no one don't want it.
Well, I think if we so we mentioned in some of our workshops before vignettes, so relevant vignettes of whoever it is the end user, and around those, then you say, well, what would we be delivering? What do they want? And then it's all the technology stack and the science stack that you need to deliver the best possible outcome to resolve that use case or that use vignette. No? Is that a suggestion?
Yes, I think really get the feedback on how you use this intelligence, like if I give you this range of frequency you can use, is it useful? Like, is it something that you want to know in advance, and how long in advance you want to know? Or if we have a nowcast system of GNSS, I talked to some of the expert on navigation. They say, we never rely on one method for navigation, right? So who wants to go to car only based on GPS navigation? So there were a lot of methods. So that basically tell me that the nowcast of particular system might not be useful. But but they say maybe if you tell me 1 hour in advance, that'll be useful. So that'll be a target that we can go after. And that's the job of scientists and physicists, how to improve that direction. So I think define who is using it and how they use that information is so critical to get those feedback back to some of this Space Weather Forecast Center.
Yep. Carlo want to say something?
Sorry.
Yes, thank you. Just to say that, in my opinion, just using the experience that we have also in other fields, for example, related to the space exploration, which I'm working in any case, it is important what was said before about the users. I think that we have to start from the users and try to understand what are the priority services which are needed in warfare scenarios, or also in other than warfare scenarios if you want. And this can be selected or indicated by the main stakeholders that in case, and that in case could be, let's say, the peoples involved in this kind of operations. And in that case, we can make some, let's say, assessment about the criticalities. So we have to develop something which can help us to identify the level for each of these priority service, the level of criticalities, and also the assessment, the safety assessment of the critical assessment that was just in some sense also described by Professor Messerotti before. This is a good idea, just to give priorities, because if we go on the models, on the physics of the problems, we have a lot of activities that have to be studied, a lot of topics, and we could have, let's say, the problem that there are so many things that have to be analyzed, that we will not focus on the operational aspects. So in general, I would prefer to have, let's say, a more, let's say, focused approach on some specific and priority services and try to assess the impact of space weather on these services, which can be of high priorities for the activity that we have to study, to discuss, to try to find. It's at least this is the experience that we have also in other field of we are now, you know, probably all the world is more or less working on this lunar CNS, which is communication navigation service, which is now on the a very hot topic. And the approach that we are trying to follow is exactly the same, to focus on the, let's say, vital services which are really needed, and then to go to additional assessment to identify additional services. But the priority is has to be taken from the users, from the people who are on the battlefield, for the people who are involved in the operations, because they know what is really critical for them. If they lose communication, probably they are completely lost, and this is not good at all. This is more or less the approach, just to give a perimeter to the activity. At least this is my small contribution to the discussion.
Thank you, Carlo. Dan?
So I think what I've heard are a couple of things that we've mentioned before, right? It's to find a better forum. That is one way to enhance coordination. It's really to pull the operators in. It's potentially an operational vignette. Why don't we do this? Why don't we determine what kind of orbit we're looking for and what kind of mission capability we want to discuss? I think if you kind of narrow it down, right, that will enable me to make some phone calls and at least try and bring some operators in. For example, if we want to do GPS, I can try and make a phone call out to the GPS squadron out in the US and see if I can get an operator or two on board, right? And what all that does is we're simply trying to narrow it down to what are the data parameters that we're looking for, what are the impacts, kind of, you know, I think if we can define the problem a little bit better, or at least narrow what we are looking for, that might be a way to kind of get a solution a little bit faster, if that makes sense. I feel like we're spinning our wheels a little bit. I think the value of a NATO organization is really to try and coordinate and understand capabilities across all the nations. But I think if we bound it a little bit, then we can kind of look at it problem in more detail. You know, so GPS, for example, you would look primarily what MEO. I mean, but any of the satellite systems we could look at trying to refine. So I guess I would collectively ask the team to, you know, provide some feedback on that. Over.
Sure. Yeah, I'm sorry. I lost sentence. Yes, Dan. I think that
I said something brilliant. When you faded out, it was something brilliant.
Okay, I see the raised hands, but I'm not sure that it's an old raised hand, or you want again to say something.
Angela, did you have another comment?
Angela?
No, I think I'm saying I agree. I think we're getting there. I think we're honing in on what we need to do, and I was just agreeing with everything. It was a lazy hand, actually. I hadn't taken my hand down from last time. So.
Okay, I see that we have a lot of things to do, and we can, yeah. Now, Angela, do you want to? No, okay. Please remove the hand. We can talk a lot, but I think that this first food for thought, what the intention of this workshop already for the second day of our conference. I think that we achieved the main idea to start thinking what, how, and when, and how to continue, what kind of models, and etc. And I think that we agreed in a lot of things. The beneficial for me was that we already have. What, Dan? You have something?
No, I was just capturing that as an action for myself. Right, if we're going to narrow down the space of what we're looking for, no pun intended, if we're going to narrow down what we were looking for, right, if we find a specific use case, I can reach out to the GPS squadron commander, I can reach out to the GPS commander, and have a conversation and see if I can bring somebody on board to have a conversation with us at our next meeting.
Yes, and we will have, that was the idea of this discussion, actually, to start on the next stage, actually, because we 6 months, we will more listening, more some kind of assessment, some kind of orientation process. Our intention we done was for this conference, for this workshop, is exactly to see what to do for the next 6 months, just to move forward on the group and to continue. We raised a lot of additional questions, a lot of additional information, and for me is quite good and really useful that was workshop, and we can continue forward. I would like, just before to end this workshop, to every one of you to say something finally, and something what to put inside, and to thinking, and final thoughts, actually. Let's start with who? With Gwen. Gwen? Something final? Something like round table? You want to say something? We cannot hear you. You unmute your mic. Just say, okay, I don't have something else.
You mean me or?
Yes.
Yeah, okay. Well, I think it was quite interesting. Also to see the event, also to see. I think it's already mentioned. It's important to get the more into the and get it more regional. Also,
unfortunately, we cannot hear you very well. We cannot hear you very well. But anyway, after this workshop, please, every one of you to write something and to send to me, to Dan, to Ralica, and we will summarize all thoughts from this workshop. Okay, Kostadin, your final.
Thank you, sir. I heard very interesting things, and
it's better now, or?
Yes, we cannot hear you.
Okay.
It's some kind of flunk. Yes.
Okay, sorry.
So it was interesting and beneficial for
There's
me.
a delay. I cannot make anything.
Yes. Okay. Let's try again with you. Okay. Please say your final words.
Well, I think it's delayed. I cannot.
Never is too late. Come on.
Well, if I tell you something, it's delayed. So for me, it was really nice to see the models and to learn how far they are evolved already. And I think, as we said, must go more, even more into operation. So I would like to see also in future to have more regional resolution, temporal resolution, higher temporal resolution, which then is really directly usable by many applications, for instance, for GPS. So if you know your region and you have a dedicated forecast, then you can work with this information. And I think we are on the right way, and it was quite interesting and was a very nice conference. Thanks.
Thank you. Thank you, Hans. Now, Kostadin, you can continue.
Thank you, sir, again. I think that we have many different possible directions in which we could make our researches and to have some results valuable for the military or the civilian part of the world. During the conversation, different ideas came to me, and probably I will share with the team later. Just as an example, during our daily routine work in our Center of Excellence, we realized that if we're capable to model and simulate every specific tactical level task in limited time and space, we can achieve results on operational and even strategic level. That's why such knowledge, as it was already mentioned during the conversation about space weather, is very valuable for us also. And the other thing, when we have such a model, it could be used as input data for another models representing another processes. And why it's valuable? Because most of the data is contaminated, let's say, with specific noise. Some source of this noise is actually the space weather. That's why modeling it, of course, is something very valuable for other scientists and engineers.
Yeah, thank you. I hope that one day we will not simulate the director of the center. Okay. Thank you, Kostadin. Let's continue with Professor Massarotti. Are you still here? I cannot see you. Could you give me the list?
Yes, I am here, yes.
Yes, please.
Well, it is difficult to summarize all the points that have been raised. The scenario is complex. That's the, say, major matter of fact. The point is up to what limit do we want to push the goal of this working group or, say, action? What I can see is the dichotomy that we have between the civilian applications and the military ones. So I don't think that one can make a sort of set of recommendations that are universal, that is devoted to both the civilian and the military world. On the other hand, what you can do is making a review based on use cases, real use cases for military applications, and judge what are the services that are provided by the different institutions, agencies, and so on, and find out, identify the gaps. You can say, okay, this is provided by the Space Weather Prediction Center, which is one of the richest set of services that are provided worldwide. And if you consider that, then of course you can identify what you would like to have more or more focused or in a different way. And this is the way I would proceed, starting from existing models that are used in operations. For example, the ones by the Space Weather Prediction Center, or for example, the space weather segment of the ESA SSA, because they have a lot of services, 155 services that are coordinated. And so you can see if what is provided is sufficient, if you need something more, making a sort of cross, say, combination between the Space Weather Prediction Center services and the ESA services, just as an exercise. I don't know if this is feasible or if this is a methodology that you would like to start or to continue and so on.
Mm-hmm.
I am over. I don't have other, say, brainstormings.
Yeah. Thank you. Actually, we already started. Maybe I think that Colonel Galton mentioned in the beginning that we already provide some kind of questionnaire to fill out from the national point of view, and we already have some of this questionnaire, and we have some nations. That is exactly what where we started. And we would like to use this year exactly for this one to use to collect the information from nations' point of view, and after that from other organizations, and to see what is on the market, what we have it. Yes, definitely we should define more gaps and to see where should focus some efforts. Okay, Sean, are you here? Sean Young?
Yes, I'm here.
Do you have something to mention?
Sure. Yes, this has been very interesting. I've enjoyed the talks. Unfortunately, I've had to come and go a little bit. I think that one thing that I hope that we can do in the future is look at what is already being done in different nations, and identify ways that we can collaborate together, understand each other's approaches, capabilities, and move forward in that way. I know that there's a lot of efforts that sort of parallel what we're talking about today here around the world in different nations. It would be sad if we spent the time that we have trying to recreate what they're doing, but it would be really nice if we could identify how we can bring everybody together in a way that only NATO can, and understand each other's capabilities and what their perspectives and views are, and how they're going to go forward. I really do think this is a great idea to get a lot of operators in here, talking to them and understanding their capabilities or their desires and their needs as well. But yes, this seems like a great effort, and I hope that we can keep moving forward and make something of this.
Thank you, Sean. Claudio, your final thoughts? Claudio, your thoughts final? Okay, let's continue with Dr. Funk. Dr. Funk, I don't want to miss you.
Hi.
I would like to attract you actually to continue to participate in our group.
Yeah, thanks for the opportunity. I mean, I was kind of last minute get into this group. I don't know how much authority, and I also have limited knowledge that I feel with this broad space weather problems. So I will try to summarize what we get today and then bring it back to Noah to see how we can support these activities. I'm sure we will be happy to continue support modeling perspective, and we look forward to hear more feedback from the user perspective. Thanks.
Okay, thank you. Angela.
I'm just unmuting. So I would say to you, I speak on behalf of Cyril. Has been watching all of this. He just, he's actually quite shy of camera, etc. So Dr. Cyril Matisse has actually been with us all throughout and commenting. For me and for us, this grouping is incredibly important. NATO. If you sat where we sit at the moment in Scotland, in Britain, with looking at sort of the turmoil of some of the decisions that are made in this country in the last year or several 4 years, the need to come together. I think the need to gather. NATO is seen by a lot of, and I don't just talk at a personal level, but I talk about it as a strategic level for the country as well. It's really, really important. But I think the subjects that were touched upon as well. I mean, what a privilege for us all to have this competence on this in this program. And I'm being high level, but I'm going to come down to the pragmatic. But we talked about, the impact of space weather on society. I think our two colleagues presented, the impact on society, on population movement, if space weather, impacts all sorts of societal and population. And Mauro suggested a paper, A Day Without Space. I think we've all gone through a very interesting experiment of 16 months of not knowing whether we can even talk to our neighbors without, dying of a disease. So I think there's something there's an opportunity here that we have that gives us urgency and pertinence. And then we come to what? And I think it was great at the end. We need the use cases. So we have to hone in. We can't boil the ocean. So let's get some pertinent use cases and I think also the idea of what are the services, what are the gaps. Try and triangulate that, and then decide what is the science and the data that's needed to come from there. So that's my outtake, and it's been a really dynamic, despite the medium that we've had to speak to each other on. It's been a dynamic and a very informative coming together of a lot of really great thinking. And I think the science that has been presented is hopeful, very, very hopeful. It shows that a lot can be, we do have the means. Humanity has the means to address these. I'm very optimistic on that. I leave here tonight thinking that too. Over.
Thank you, Angela, for your thoughts. Actually, they are very, 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 very valuable, and I share your thoughts, of course. Just before to give the floor to Dan for final remarks and summarizing this workshop, I'm worried if I miss someone. Is there someone who I'm missing? I've missed to say his final words? No. Then I agree with everything what happened. I would like to thank you to all of you for participation in this in our conference in CMDR and to be your host. But after this discussion, my opinion is that we need face-to-face meeting. It's very difficult to work online, and really we need a glass of wine and to sit down and to talk even 3-4 in one time, and maybe we will have a much faster forward. Yes, and my invitation is the first face-to-face meeting to be organized here in Sofia in Bulgaria is still on the table, and I'm ready to organize it. Just we should decide this COVID measures and everything when will be finished. But I really hope that soon. We already conducted actually even this is the third event, hybrid mode, online and in participating mode here in the hall in Sofia, and it's quite successful and and safe, yes, and safe. Well, yes, of course, everything is safe when we keep the measures and be in mind, one in mind. From that perspective, I think that we achieved. Thank you to all presenters, and just to remind you that everything is recorded and you can download it from YouTube channel on the CMDR COE and to follow again and to take notes if you miss something or if you would like to remind something. With that, I finish my part. Dan, I give the floor to you for closing remarks and closing thoughts.
Okay, so I will add my thank you as well. I think this was a very good conversation today. It was not an easy conversation. I think we had a lot of good discussions. A lot of really good points were brought up. We talk about complexity. We talk about complexity of the system. We talk about complexity of the question and what we are trying to address. And so there are no easy answers, but I think we are making progress, which is encouraging. I will encourage everybody to continue to be proactive, to try and think about the problem, where we can improve our discussions, where we can improve our products and our methodology. But with that, that's your homework. So as you leave here, think about how you can fix this. But I simply want to just say one last time, thank you. Have a good rest of your day or a great evening. no matter where you are. Orlin, will we have a summary or some minutes coming out of the discussion from today?
Yes, we will provide it some kind of minutes from today, and we will try to summarize what we talk. Maybe I'll try it just like a minutes to be, and everyone to read it, and to summarize maybe as a final results from the group.
Okay. We can take the conversation offline, but maybe we look at having one more meeting before the summer holidays kick in August. But we can, like I said, we can take that offline. But I'll simply close by saying thank you, everybody. Have a good rest of your day, rest of your evening. And I like Orlin, look forward to meeting everybody in person one day. So thank you again.
Thank you. Thank you very much.
Thank you very much.
And
Thank you all.
be safe.
Bye. Thank you.
Bye.
Bye.
Bye. Okay, take care.
Thank you. And all of you, please, all our guests are invited to participate in our group. You will receive our invitations for the next meetings.
Thank you. Goodbye.
Thank
Bye
you.
bye.
Bye all.
Okay.
Bye. Thank you very much.